Hey, good morning, everyone.
Morning.
Morning.
Morning, sir.
Good morning. Good morning, Jiaming. And I can make out H and Henry and
Good morning, sir.
good morning, Shetal. Let's wait for around 3 to 4 minutes. Let's more people join and then we can start. Okay, good morning, everyone. So, welcome to the block 2 of the advanced water and wastewater treatment 42991 subject. Yeah, my name is Shera Punsu, and I'm a senior lecturer at the School and Civil and Environmental Engineering. So, before we start, I just want to know you can hear me properly. Can someone confirm me?
Yes, we
Yeah,
can hear you.
Great,
yes,
thank you. I'm sure some of you must have already gone through the video. So just anyway, I'll introduce briefly myself. Yeah, so I've been working at UTS since 2012 after completing my PhD. And my undergraduate background is in civil engineering, and I, I have my undergraduate degree from India, and that was a long time ago. And then I did my master's and both PhD at UTS in environmental engineering. So my field experience is also related to environmental engineering. So that's how I got interested in related to water, wastewater, and so yeah, I've been teaching this subject for last I think 5 years, and a couple of years I even coordinated this subject. So now I'm sharing the subject with Professor Sean and Dr. Leonard Tejing. So yeah, I introduced myself. So I'm meeting you all for the first time. So I would appreciate if you could, if you don't mind, putting on your camera and then introducing, so that at least I know whom I'm talking to, and then so to know each other, because today it's a long lecture. So yeah, I think it's great to know each other. Maybe who wants to start? Maybe you can put on your camera. That would be great. Great. Maybe Amit, you can start.
Yeah, good morning, Professor. My name is Amit Hassan. My nickname is Shishir. I am from Bangladesh, and my background is I have completed my undergraduate degree in civil engineering and currently doing my master's in management in engineering management as environmental engineering as major. And I have around worked in wastewater treatment plant projects for 2 years and still working from overseas. So yes, this is my background, and I'm looking forward to have a nice session with you.
Okay, so you're still overseas, or you're in
No,
Sydney, Australia?
I'm currently Australia, but I'm working from here actually.
I see, I see. Okay, great. Thank you, Amit. Okay, have Sagar next.
Hello, Professor. I am Sagar Bakhunse. I am from Nepal, and currently I am in Sydney. I am studying my Master of Engineering Structure. I am in first semester of my study, and I have worked as civil engineer for about 4 years in my home country. Thank you. That's it.
Great. Thank you, Sagar. Nice to meet you.
Thank you.
Ella.
Hi, so I'm Ella. I'm currently doing my 4th year of civil engineering, and I'm currently working at Sydney's International Speedway.
Oh, Sydney International Speedway.
In Eastern Creek.
Is it the infrastructure project? Yeah.
Yep, it's
What's
almost done. We're just doing defects
uh,
right now.
I see. Great. Okay, nice to meet you, Ella.
Nice to meet you too. Thank you.
Okay. Yeah, thank you. How about, okay, Jiaming, you want to show your face, and then others want to share your story or your introduction?
yeah. Sorry, Professor, I have some problem with my camera, so
Okay.
I can. Yeah.
Okay,
So
maybe.
my name is Jimmy. Yeah, I'm come from China, and my major is civil engineering. So I'm very glad to enjoy the class with you, Professor. So
Okay. So you're in Australia or you're in China?
no, I'm overseas now.
Okay. Okay. I see. I
Yeah,
understand.
you
Okay.
know, because of COVID-19, so
Yeah.
I can't come to Australia.
Okay. I see. Yeah. Okay. Sad to hear that. But hopefully things will change, improve. Let's
Yeah.
hope. Yeah. Okay. Anmar.
Hello, my name is Anmar, and I finished my bachelor's in civil engineering back in my home country, Jordan, and now I'm doing my master's in environmental engineering. It's still
Okay.
my first year doing
Uh,
master's.
so you are here in Sydney, right?
Yes, I'm in Sydney right now.
I see. I see. From Jordan. Okay. Great. Nice to meet you, Anmar.
Thank you, sir.
Okay. So any other, maybe Mitch? Mitch, you want to introduce yourself?
Yeah, hi, I'm Mitch. I'm in my fourth year of civil and environmental engineering.
I see.
Yeah.
Okay. So you're undergraduate. So you're finishing next year, or?
Hopefully, yes.
Okay, I see. Okay, nice to meet you, Mitch.
You too?
Okay, Laslan.
Yeah, hey sir. I'm Lachlan. I'm doing a Bachelor of Engineering and majoring in Civil Environmental, fourth year. And yeah, chose this subject because it seems really interesting and I can see myself doing that in the future.
Okay. Okay, great. Thank you, Laslan. I think we have last one is Paige Webley.
Hi, I'm in my last year of civil environmental engineering and I work in construction project management. And I'm from Queensland.
I think you attended one of my previous classes, right?
I was in a
Is it?
class of yours last year. I think it was like a similar one to do with water.
Okay. I remember. Okay, that's fine. Nice to meet you again, Paige.
Nice to meet you too.
Okay, so that's a good thing we know each other now. We're from Bangladesh, we're from Nepal, we're from China. So most is from Jordan, but most of you are from here already. So it's great. Sorry that we couldn't really organize this in the face to face in the campus. So still, yeah, some people are still overseas, so that's we have to have online. And today, let me share my screen. Oh, screen two. Okay, so are you able to see my screen?
Yeah.
Okay, great. Okay, so today the block two, we may not be able to, we may not have to go till 2 o'clock, but anyway, we'll have short breaks in between. So probably after 1.5 hours, we can have a break, and then, so we'll see as the time goes how we can play with the time. Okay. Okay. So these are the topics that I wish to cover today, and as you know that the video is pre-recorded videos have already been released. So I just want to know how many of you have been able to watch this video, that recorded video. Maybe if you can raise your hand from that hand raise button in the Zoom. Okay. 1, 2. Okay, so only 2 of you. So most of you couldn't have time to listen. So that's fine. So anyway, there should be no problem because you still the some most of the things are already that you are aware, because it's just brushing off of your memory that what you have already learned before. So I will just, so when you go home, you can go listen to the videos, recorded videos again. So I have divided this one into two videos into three sections, 2A, 2B, and module 2C. So in 2A, you'll have three topics, actually: the water quality and water sources, and then surface water treatment processes. And in the second module, you have membrane processes for water and wastewater treatment. And the last one, 2C, is about the water and wastewater treatment. So that will basically be talking about differences between the conventional activity slash process and the membrane bioreactor, MBR. And also I will share some of the research works that we have been doing at UTS, so interesting ones. And we trying to treat the urine and then convert into a useful fertilizer, and in that way how we are able to benefit the treatment plant and also the environment. And then we'll talk about the assignment tasks, and then we can have some discussions if you have any questions. So as I'm talking, so it's been a long day, so at least you can interrupt anytime you want to ask questions, so then we can have interactive discussion. Okay, it's not just a one way me talking only. Yeah, agreed?
Yes.
Okay, thank you. Great. Okay, so I've just what I will do is for module 2A and especially 2A, I'll just a little bit brush up only. So please listen to the pre-recorded videos when you go back home. And 2B, I will do a little bit more, but yeah, 2C, I will a little bit in more details we'll discuss. Okay, so let's talk about the water quality and surface water, water sources and surface water treatment. So I'm sure you know the importance of the water quality, and what does water quality mean? It's basically it describes the condition of the water, and it's condition of the water in terms of how it looks, how it appears, how it smells, and how it tastes. So it's basically trying to understand the characteristics of the water. So when you can go in further details as to what sort of composition the water has, what sort of physical qualities it has. So all this constitutes the quality of the water. Okay, and then of course it determines also whether the water is polluted or not polluted. And as you know that the because of the the anthropogenic activity. So anthropogenic activities means like the activities of the people, right? So because of that, it has really impacted the water cycle, and because of this, we have a lot of water scarcity in all around the world. And also the climate is changing, and when the climate is changing, the water cycle, that normal water cycle that we have, is also changing. So where there is no rain, there's a lot of rainfall happening, flood happening. When there used to be a constant rain, there's drought happening, very prolonged drought. So all this natural water cycle has been disturbed because of the change in the climate. And also the change in climate has been already proved that it's related to the activities of the humans living in the earth, that we are emitting so much carbon dioxide, and that's causing the greenhouse gas emission and also global warming, and that resulting in this change in the climate. Okay, of course there are natural causes of the climate change, but natural causes has been happening for a very long time, and it never really impacted the earth seriously. But nowadays it's becoming more serious because in the top of that natural climate change, the man-made climate change is severely impacting. So if you can see this water cycle, you have seen law in natural water cycle. You have you take the water, it goes the water, it goes evaporated, it condenses, come back, and just keeps circling, right? But the problem here is you can see that we have, because of human activities, we have been releasing so much, taking out so much water from the natural sources, over exploitation, and then we are polluting the water and then putting it back. So in that way, really, really damaging the environment. So water quality is very important. So for the water managers, so that we know where the sources of water is polluted, where it has to be concentrated to aim at in treatment and those sort of things. So water management, for the water management, the water quality is quite critical. Okay. And so these are some of the properties that are of importance. Broadly speaking here, say, okay, physical properties that relates to color, odor, the turbidity, that's appearance also, and then temperature. So this is basically the public perception, because when you look at the water, if it's a bit murky or the color is a little different and not clear, then you suspect, oh, there's something wrong with the quality. So that's you have to, that we can able to perceive with our senses, right? And yeah, of course, the temperature is quite important as well. So it impacts many other the properties of water, and the chemical properties. So that increases the water toxicity. So, and of course, some of them, most of them, you can't really even peel with your perceptions. It has to be chemically analyzed in the lab. Then only through we can understand what sort of composition it has. Maybe pesticides, phenols, the organic matter, heavy metals, the nutrients, nitrogen and phosphorus. So those things are present in the water that which you can't see. Yeah. So this this from the chemical properties and the biological properties. So the biological properties related to the biological matters like organics and of some related to plants and animals and bacteria, virus. This which may cause the health problem for us immediately. Some of the chemicals, for example, up there, it's not really in big concentration. It can be a long-term effect, but biological properties can be immediate effect. So if the water is infected with virus or the bacteria, Escherichia E. coli or something like that, then you immediately can have dysentery, diarrhea, and the impact is quite immediate. And we have there's a definition for palatable and potable one. Palatable is something that you can aesthetically pleasing water that you can, okay, this is drinkable water sources. But potable is something that it is safe to drink. So once you treat it, then it becomes a potable water. So then this Dr. Lena teaching has really described all this very well in the video. So please listen to the video for if you want to know more. Okay. And broadly, when you talk about the water quality parameters that we measure, usually these are the major, I would say, broad the parameters that we use or indicators to check the water quality parameters. Okay, so pH is one. So pH are some of the range of pH expected are given. If the pH is deviating from within this range, that means there's something wrong with your water. Okay, hardness, this is how much how much calcium and magnesium is present in the water, and because it can really impact the water use when we especially work using the water for laundry or shower, because it can the soap will not really lather well. So that's why it's important that the water hardness is within that range. If it's very hard water, then yeah, you'll have to treat it to remove the hardness. Salinity is one. Salinity and total dissolved solids are related. Salinity is how much salt it is contained in the. It's measured also in terms of electrical conductivity, and total dissolved solids are also measured in terms of conductivity, and you can convert it into how much salt is dissolved in that. So that also impacts the quality of water. If it's too saline or which is too salty, and then the water is not really the potable. So it'll have to be salt has to be removed, right? And temperature, as I said, temperature really impacts the water quality. It can impact the pH, it can impact the hardness, because as the temperature increases, some of the compounds that's present in water will become more soluble, some will become less soluble. So in that way, it will impact the total dissolved solid, electrical conductivity, etc. And also it can impact the dissolved oxygen, because okay, see, when the water is warm, it can release the oxygen, because it it heated up and the oxygen can be released. So in that way, the dissolved oxygen concentration in the water can also change. Okay, And there's also biological oxygen demand and nutrients. Biological oxygen demand, as you know, is about related to organics, biologically degradable organics, right? Okay, am I recording this? Because I can someone see that it's recording?
Yeah.
It's recording, right? Okay, sorry. Okay, so yeah, then yeah, so biologically, degradable organics. So this the presence in that can be also a quite problem for water because it can become smelly, and then it can it cause a problem within the what's the pipeline. So those things are also important. And nutrients, of course, the nitrogen and phosphorus present in. So you can't, if you have there's too much nitrate, then that's also not good because you have what you call a blue baby syndrome that impact the young babies. Okay, so these are some of the quality parameters for Australian drinking water standard that's obtained from the usually this most of the water quality guidelines are based on the World Health Organization WHO water drinking water standards. So Australian one is also a bit similar to that. So you can check it, and then yeah, in many countries they either have their own drinking water standards, and also most of them are based on the WHO guidelines. And but some countries they don't have, and then they use WHO guideline as the reference standard. So these are some of the concentration that you should be expecting in the water for for the water to be a standard drinkable or potable water that you can supply for drinking purposes. If it is deviating from this range, then that means your quality is not good, and then that you have to have a treatment to remove, for example, turbidity. It should be less than 5 NTU. If it is more than that, then that means your water is more turbid, and then you'll have to do to remove the suspended solids. Okay. Can I have some meeting here? And about the water quality and the type and the sources of water. So there are various water sources that you can use it for your treatment and application for supply for different applications. So groundwater is definitely one. The many countries are depending on that. And of course, the groundwater is supposed to be one of the cleanest water sources because it's naturally filtered and then through the soil, and it's very pristine conditions in the what aquifers underground. But of course, with a lot of human activities, with a lot of agricultural activities, the nutrients are seeping inside, and then also it puts impacting the water quality as well, even the groundwater. And surface water, of course, the many countries depend on the surface water sources for their drinking water purposes. Is exactly for here in Sydney, for example. This is, I think, the Warringah Dam in Sydney. Here, I think so. Should be Warringah Dam. Yeah. So yeah, this is a source of surface water. So we dam it, and then the rainwater that we get and the streams, and then this is collected, and then we use this as a source of water supply for the city of Sydney. And stormwater also, of course, you can use it for various purposes. Also use some stormwater harvesting is going on in many cities in Australia. They have this from stormwater ponds, collection ponds in many areas, and then they treat this one through natural source, naturally filtration, and then they use it for even for the watering the lawns and those sort of things. Okay. Seawater is, yes, of course, one of the most reliable source of water because seawater is plenty. We know that the earth's water, 97% is the seawater. Okay, so which means we have huge amount of seawater. It's a very reliable source of water for the people living in the coastal areas. But of course, you can't drink the seawater immediately, right? Because it is a very high salt concentration. But we have technology that can convert seawater into drinking water through desalination. So we have a lot of desalination. When you talk about, maybe you have think about distillation. That's one, of course, but distillation is very energy demanding process. So that's why we have membrane process, what we call reverse osmosis process, where we desalinate water and then supply. So we have in Sydney a desalination plant, where of course we never had to use, only I think before last year we had to start because of the drought. We have to start for a few months, but yeah, then we didn't have to really operate that. But it's many in the Middle Eastern countries where the water is scarce, the desalination is the main source of water. Of course, brackish water, it can be brackish lake water, the groundwater. So it's also a source of water, but we need a treatment. Nowadays, the wastewater is becoming also a very, very reliable source of water. You know, as long as people are living, people have to drink water, they have to use water, and wastewater will be continuously generated as long as people are living in the city. So that is a really reliable source of water as well. So only thing is it's highly polluted. So, but we have to treat anyway. So when you treat it and then you have advanced treatment, you have additional treatment. So and then conventional treatment process, and then through that you have advanced treatment. Then we can make this water as a very good source for non-potable purposes, so that you don't have to depend on the fresh water for those applications where very high quality of water is not required. Okay, so that's also the purpose of this subject: advanced water and wastewater treatment. Okay, any questions so far? Okay, if not, so let's okay, so this is the range of the water quality that you expect from a domestic wastewater, the sewage that you get for the treatment. If you look at the BOD, the biological oxygen demand, the organic carbon, let's say the organics present in the wastewater is very high, say up to 300 milligram per liter. It's all because this wastewater coming from the toilet, yeah, flushing from the toilet. Then you have people, let's say, taking shower, the laundry, and then washing in the kitchen. All this contribute to the BOD. And also COD is even very high, see 1000 milligram per liter. That shows that this 1000 minus 300, so 700 milligram per liter of organics is present in water is not biologically degradable, so it has to be removed. So it may be some inorganic carbon present in that. Suspended solid is very high, 350 milligram per liter. That is showing it's very highly turbid. And total dissolved solids even up to 1000 milligram per liter. From 200 to 1000. 200 is low, 1000 is quite high. So it's even if you treat to 1000 is not the drinkable water quality that you can obtain. So it's okay to be used for irrigation and other for cattle and those sort of things. But yeah, not really. Even if you do irrigation, you'll have to be a bit careful because the salt can accumulate on the plants and then you can have a problem. So we had an incident where in one of the councils, before they invited us to see the water quality, because they were seeing all these white patches of deposits on the plants that they were using the recycled water for irrigation, and then we realized that there was all these white patches were the salt accumulation because the salinity of the treated wastewater was quite high. So those sort of problem can happen. Okay, so that ends the surface, the water quality and the water sources. So there's next surface water treatment processes. So I'm a little bit divided into surface water treatment and wastewater treatment, because the difference you will see is the wastewater is more of organic treatment, and whereas surface water is more of inorganic suspended salt and those sort of things. So if you look at the water, the difference between water and wastewater, of course, water, the source is coming from the fresh water, natural sources, whereas wastewater is after the water has been used and is a part of sewage or industrial waste or the stormwater or the agricultural waste coming. Why the treatment is required? Because we have to remove, for water, we have to remove contaminants that can cause disease, such as if it's microorganism present or any other chemicals present, you can't supply it for drinking purposes. So that's why we have to treat, disinfect, and also remove that can cause nuisance like odor, color, and all. But the wastewater we have to treat because it has a lot of organics, BOD and COD, and the suspended solids, nutrients that will pollute the environment. So that's the reason that we have to treat it, right? And the treatment goal, treatment goal is to make surface water treatment, to make the water potable or safe to drink, and also look it very pleasant and in appearance, taste, and odor, so that it's not that's something, oh yeah, this water is not really, doesn't seem to be good, right? So in order to avoid those sort of thinking, so yeah, that's the reason for treatment of the water, surface water. But for wastewater, it's required by law, by the legislation, that you have to treat, because you can't discharge the wastewater. So the legislation is basically to reduce the environmental pollution. And of course, also you treat better in advanced treatment in order to reclaim the water, recycle the water, and reuse it. So these are some of the fundamental processes that's involved. I'm sure you have learned this one in the undergraduate studies, and also some little bit in the high school. So there are three major processes that treats the water. So the physical processes, chemical processes, and biological process. Physical process actually depends on the physical forces, like for example, the gravity, or that you apply pressure, or that you physically strain them. So such as screening and mixing, flocculation, flotation, then filtration, sedimentation, etc. So sedimentation, you are basically using the gravitational forces to let the particles settle. So in that way, we're using the natural physical process, to natural and the applied forces to treat the water and wastewater. And chemical process, of course, we add chemicals. So in the process, what can happen is chemical reaction between the pollutant and the chemicals that you add will result in either precipitation, coagulation, absorption, or oxidation, or disinfection, killing the bacteria, organisms, or even decomposition of the bacteria, the organics present in it. So this is the chemically transforming the compounds. So this is the chemical process involved. And biological processes, it's anything that's biodegradable, that the microorganisms will work. So nature has given a very unique way of sustaining the environment on this earth. Imagine if there was no bacteria that feeds on the organics. This world would have been filled with organics, the dead bodies, right? So when you put the dead, let's say for example, animal carcass lying down in the open, so within a few days, it's only just bones and bones left, right? So everything is the flesh is gone. So this is the nature is really the bacteria is eating up everything. So we learn from that, okay? And then this is what we apply for wastewater treatment. So we use these microorganisms to help us to clean our wastewater. Yeah. And by doing so, this the bacteria can help in not only in converting and remove the organics from the wastewater, but also in the process sometimes helping to generate energy. For example, if you do anaerobic process, where organics are anaerobically digested, and it can even generate energy in the form of biogas, like the methane, and then we can use this one for cooking and those sort of things. So these are one of the beneficial uses that we apply for water and wastewater treatment. So water cycle in the domestic water uses. So you have a surface water here. Okay, we treat through various processes. Yeah, various processes, because any water treatment or wastewater treatment process, you can't have just one process to treat. It has to be a series of treatment, stage by stage, because there's no. Of course, if your water quality is very clean, like for example groundwater or a very undisturbed stream water, so maybe the treatment required is quite few steps only. But naturally, usually the process is plenty. Usually it's a series of treatment, one after the other. So finally, you get the best safe drinking water. So you have the series of treatment and then supply it to the household. We use the water, becomes a wastewater, relays as a sewage, and then again it has to go to the same process of treatment. But in this process, the additional process you have here, you'll see, is the biological treatment, because when you, after we use the water in the houses, what we add is a lot of other chemicals as well as the organics, and mainly from the feces and the urine. So that's how we have to have additional biological treatment process before we release back to the environment. And if you want to reuse this water, then you'll have to go through advanced treatment, additional treatment process, and recycle and reuse the water. So these are some of the process treatment trains, like treatment train that is used for the surface water treatment. So you have, okay, raw water, say maybe this is let's say the river water maybe, and river water is not because most of the rivers flow from very, very far, long distance, and then in the process they can collect all the dirt and everything, so there is very high concentration of suspended solids, and it can also dissolve to solids. So, and also it can contain a lot of, large pieces of objects that's carrying it, let's say wood and those sort of things. So the raw water is first passed through a bar screen to remove large objects, okay, bar screen. And then after that, it goes to the grit chamber, and basically to remove all this high density, let's say, high density inert particles like sand particles or other grit particles. So that this, because if you don't remove those things, then it will impact your pumps in the treatment process, because in the treatment plants, usually in most of the treatment plants are lying on the flat area. So it usually it doesn't really work with the gravity flow. So it has to be, to flow from one process to the other process, usually a pump is used. And if there are a lot of silt and large inner particles, then it can damage the plant. So it has to be removed. So grit chamber does that work, okay? And then you have rapid mixing, coagulation. We add a coagulation, some chemicals like alum or ferric sulfate or ferric chloride, so that this will coagulate, it will destabilize the suspended solid, because suspended solid, as you know, when if the river water, if you just put it in the cup and then put it on the table, and you see that it takes a lot of time to settle. Okay, large cell particles will settle immediately, but very fine suspended particle, it takes days to settle. So you can't, in the treatment plant, you can't wait for days to treat it. And also, if you do that, you require very, very huge area. So, but we want to, treat within a very small confined, with a limited space. So in this case, what you do is that you add chemicals to destabilize the particles, okay, and then destabilize the particles, and then what first you do is a rapid mixing, and then followed by slow mixing. So when the slow mixing means, once it is destabilized, then they want all these destabilized particles to form a larger flock, and then they combine together, become heavier, and then they will settle. And whatever that's not settled, they will still there will be some fine particles, fine flocks, and they go to sedimentation tank and then let it settle. And from there, whatever is settled, the clear water goes to the next stage. Sometimes you may not require filtration, but usually filtration is provided there. But this filtration is like a sand filtration or multimedia filtration. And then, whatever flock, small particles that's not removed, including suspended particles, then filtration will remove. And then you get a clean water that is potable water, and through disinfection, you add, say, for example, chlorine air, and then you supply it for drinking purposes. So this is the very generic, the most commonly widely adopted surface water treatment trains that you will see in many countries you go. This bar skin is all the time, has to be there, otherwise it will choke your what's it, the pipelines, grid chamber to protect this. So usually baskets and grid chamber are there all the time. But the next processes, it depends on the water quality. Some may have rapid mixing, some may not have, some may have filtration, some may not have. So all those combination depend on the quality of your surface water. something over here. Okay, here. See. So this is the okay. This is just a repetition of what we have done. What I have presented earlier. So it's just the screen here. You will see you have rapid mixing over here. The grid will be somewhere here, and then remove the grid chamber. Yeah, the grid. Then we have flash mixing here, rapid mixing. Then you have coagulation, flocculation here, where the frogs are formed, and then we sediment here. Okay, sedimentation, and then goes to the filtration and ultimately disinfect and then send it for storage and then and water supplies. Okay, so this is just a basically animated chamber block. So there are other various combination yeah, we can have for surface water treatment depending on the quality of water. So for example, you can, if the water quality is very clean, say for example, the groundwater, if the groundwater is not contaminated, very clean, very low turbidity, and then yeah, you don't have to really do the treatment. So usually people supply it like that. So, but just you to have at least disinfection, chlorination to ensure that you know if there's any microorganisms present there that will be killed, disinfected, or even if they don't have the bacteria in the process of the transmission from the source to the consumer, we just go through a long pipelines, right? So when you go through the long pipelines, it's sometimes possible that on the way it can be infected with the bacteria and also so contaminated. So in order to prevent that, you have to have some residual chlorine within inside the water. So that's why chlorination is there. So in before, I think long time before, Sydney Water used to supply like that. They didn't really have to treat the water because the water quality was quite good. So they used to do only the chlorine and then supply. But after later on, they have to have this. Now they have a full treatment processes. And the other one is just the filtration. Okay, you don't have to have any other mixing or anything, and you just have to have. There may be a little bit of suspended solid. The quality of water is a little bit worse than the first one, and then but it's still relatively clean. So in that case, you can just use the filtration and disinfection and filtration. And you can use sand or the coal for filtration. But there's another one they call inline filtration. If the water quality is little even not that good, then you have to, instead of having a separate coagulation tank and a separate filtration tank, you can just have coagulation added in line. So that's called inline filtration. So the coagulant will be added here, and then in the process, by the time it comes here, so whatever little suspended solids that they have, there will be, let's say, smaller flocks will be formed, and then they can be removed by just filtration and then get a clean water here. And there's a direct filtration. So inline filtration and direct filtration is similar to, bit similar to the conventional treatment that we discussed earlier, but here you don't have the coagulation, I would say all the other steps. So you don't have to have a sedimentation tank. So you add the coagulation in the above one, in the inline filtration, you don't have the flocculation, but you have to have a flocculation because you have to allow some more time for the particles to coagulate and then directly filter it and then supply it for, again, you may have to do the rechlorination here and supply it for drinking purposes. But this is a conventional treatment we have discussed earlier, where you have, of course, in all these cases, you will have to have a screen bar screen and the silt grid chamber. So you may not have to have this one if this is clean groundwater, but yeah, sometimes yeah, you can possible that even from groundwater, some particles can be pumped out. So in that way, you may have to have a grid chamber. So this is a conventional treatment that we discuss here. So you have all this bar screen, then grid chamber, then you have rapid mixing, flocculation, sedimentation, and filtration. So that's a conventional treatment plan. Okay, so that ends the section 2A. Okay, if you have any questions, let me know. Any questions so far? You can ask any question because I want this session to be interactive as possible, because some of you already worked in the wastewater or water industry. So if you have any issues, yeah, you can share with us, and then yeah, we can discuss. Okay, so if you have no questions, so then let's go to session 2. Let's say this is block 2B, okay? So this is the membrane process. So in most advanced processes, membrane process is one of the most critical processes that's been used in anywhere. Okay, so what is membrane process? It's basically a filtration. So when you, for example, we talked about the filtration using sand, coal, or multimedia. So different media can be used: anthracite, coal mixing, dual media. Only two types of the media is used. Sometimes multimedia is used, so that multimedia is better because uh, if one media doesn't filter certain kind of chemicals or some certain kind of pollutants, the other media may be able to do it. So in that way, it gives a lot of assurance and security that if one doesn't work, other will work, and so it is a combination of different the chemistries, that because when you remove by filtration, it's not just physical separation. Physical separation means by just straining, right? For example, if you have very dirty water and if you filter through using a say cloth or something like that, that the particles, the water which is very, the molecular size is very small, so they just easily pass through the filter, right? But the particles which are larger than the filter size, they will just be remaining there. So that's you physically straining it, blocking it, right? Because their size, so we call it size exclusion. You will see from it, size exclusion. There's the mechanism. And but sometimes it's not only that, because there are many other ways of interaction, surface interaction, chemistry. The surface chemistry, there may be some surface chemistry of the membrane or the filter, and also this the pollutants that's present also has a lot of chemistry, surface chemistry. So that sort of thing may interact with the within the surface chemistry and then result in removing or getting attached, or and or getting rejected. So those sort of things, the mechanisms play in the removal. So for example, electrostatic repulsion. For example, if the surface of the membrane or particle is negatively charged, right? And your organic particles, say seal particles or suspended solid particles, also negatively charged. Usually they are negatively charged in the water, because all the surface particles, if you analyze their the charges, they are all mostly negatively charged. So membrane is negatively charged, particles are negatively charged. So they, in that they repel each other, electrostatic repulsion. So in that way, they will be separated as well. So, but the membrane here, how is it different from the normal filter? Is that normal filter, you have to use like layers, very thick layer of sand, for example, like a few meters sometimes. But in the case of membranes, they are very thin. They are just a few micrometers. Say like reverse osmosis membrane, they are just around 400 400 micrometers. It's not less than 1 millimeter thick. It's less than 1 millimeter thick. It's just a 400, 300 micrometers. So that thin that we use it. And so it's membranes are semi thin and semi-permeable layer that allows solvent to pass, liquid to pass through, and then retain the particles or the dissolved particles, even if, depending on the size of the membrane pores. Okay, and it's usually used for advanced water treatment process, and also it can solve any kind of problematic water. Okay. So the membranes are also very effective in disinfection, because the in the water, it's mostly the bacteria and the virus that cause problem for us, right? The microorganisms. And if you can, they can be very effective in disinfection, because they can remove it, most of them. But then that microfilter, or we have different sizes of membrane, the pore size. So almost all the membranes will remove the bacteria, because bacteria sizes are quite large, like they are in micrometers, like 1 micrometers to maybe like 10 micrometers. They're or 100 micrometers. They're quite long, and they can be easily seen through the microscope, even with some just normal microscope. So they can easily filter. But yeah, virus is a little bit tricky because they are is much more smaller. So but that you need a more a filter that's smaller in pore size. So we have that. So even virus can be removed. So basically, you can completely disinfect the water. And also, it's membranes are very effective in removing the micropollutants. So micropollutants, we refer here to those chemicals that are present in very minor concentration, very trace concentration, we call it. Even sometimes it's hard to detect with the normal instrument. So you have to use a highly advanced instrument. But it may not cause immediate problem, but in the long term, you keep ingesting that kind of thing, it can be problematic. So in the membrane process are quite effective in removing those. So I'm talking about micropollutants, for example, pharmaceuticals. We eat a lot of medicines, right? Everybody eats medicines when they're sick, and people flush it in the excess one. They flush it in the drains, or maybe that they most of the medicines that we eat, it becomes part of your waste, like in the form of urine and the fecal matter. So ultimately, it comes to the wastewater treatment plant. And then, yeah, you can, if the concentration is relatively small, but still, it can be long-term impact would be significant. So that's why these membranes can be effective in removing those. So conventional treatment plants are not really effective in removing those kind of micropollutants. So there are different types of membrane processes, I was saying. So we have, depending on the size of the particle, the pores. So you have microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. As it goes down, the pore size decreases very. So reverse osmosis is the very small pores. Even you can't see through the microscope the pores here. Okay, so the water transport through this kind of membrane has a very completely different mechanism compared to the microfiltration. So microfiltration is a pore size somewhere between 0.1 micron to this should be around 0.4 micrometer. Okay, so it's 0.4 micrometer is like less than 1 micrometer, right? Very small. So that's the pore size that they have. So here, if you look at this diagram, it's very clear here. For example, this is suspended solid given by rate, macromolecules like proteins, multivalent ions like, for example, calcium, magnesium, and those sort of things, iron, and monovalent ions, so for example, potassium, sodium, chloride, nitrate. Those sort of things are monovalent ions, and this water. So first, the microfilter will be effective in removing mostly the suspended solids, but they cannot remove all these macromolecules, multivalent and monovalent. So they will let it pass through. So only effective in removing suspended particles. The ultrafiltration will remove suspended solid as well as the macromolecules. So like a protein. So and macromolecules can be in the size of virus and the bacteria. So ultrafiltration will remove mostly the bacteria, almost all the bacteria and the virus. And whatever this ultrafiltration can remove, nanofiltration can remove. So nanofiltration is basically remove all that is removed by the UF and MF. And if you remove even divalent ions and monovalent ions, but mostly effective in removing divalent ions or multivalent ions. For example, multivalent could be calcium, right? Magnesium, sulfate. Then you have iron in a ferric, yeah, ferrous and ferric, Fe2 plus, Fe3 plus. So they will be nanofiltration will be effective in removing all those multivalent ions. So when you talk about the water softening, hardness, if there's a lot of water hardness in the water because of the presence of calcium and magnesium, yeah, nanofiltration could be quite effective in removing that. Okay, so softening the water. And reverse osmosis is the ultimate one. So this is the finest, smallest pores that they have, and it will reject everything, almost everything. Okay, so only it let the water pass through and remove all other monovalent ions and divalent ions, even including the other very trace micropollutants. But of course, few things they still let pass through, and then you need to have a second second reverse osmosis stage to further remove it. So this is the different size of the membranes, and depending on that we have ultrafiltration membrane, microfiltration membrane, MF, UF, NF, and RO. So MF, UF, very highly porous, we call it a porous membrane, whereas nanofiltration and reverse osmosis membrane, we usually call it as a non-porous, because you can't really see their pores through the microscope. Okay. And we have some emerging membrane processes, what we call the forward osmosis process and membrane distillation. So forward osmosis is something you use the nanofiltration or reverse osmosis membrane, but in all this that we talked about, MF, UF, NF, and RO, we require energy, pressure to filter the water. So your water has to be pushed through. So especially reverse osmosis, you require very high pressure. For example, seawater. You'll see in that in block 3, Professor Sean will be discussing about the reverse osmosis desalination process. You require very high pressures, like a 60, 70 bar of pressure you'll have to apply. So that's a tremendous amount of energy that you require. So that's why seawater desalination is still very energy intensive process. So you require that physical forces to separate the thing. But here in forward osmosis, we use a natural osmotic process to, drive the water through the membrane. So that's a little bit of different way of. Then I worked for my PhD on this membrane processes. For what we used was that we used fertilizer, concentrated fertilizer, which has very high osmotic pressure, to pull water from the saline water sources, like maybe seawater or the brackish groundwater or the wastewater, and pull the water. When you pull the water from there without any energy, and in the process your fertilizer will be diluted, and when you after dilution you can use it for irrigation. So that was concept that you can use for forward osmosis process. Membrane distillation is a kind of a combination of thermal distillation plus membrane process. Okay, so in the normal distillation process, you heat the water to around over 100 degrees Celsius, let the water boil, evaporate, and then you condense the water to get the distilled water. But that's heating water up to 100 degree and more than 100 degrees is very, very energy intensive. So we call it membrane distillation, where we heat the water to around just 60 to 80 degrees Celsius, not 100, and then use the membranes, and the hydrophobic membrane we call it. They have very porous membrane, but the water will not pass through because it's a hydrophobic. It prevents the water from wetting the membrane, but only the vapor will pass through. So in that way, you separate the vapor and the water, and the vapor can be condensed. And then this is some of the emerging, the new technologies being still being tested, but not really not been really commercial in industrial scale, but pilot scale level people are still testing, and hopefully in a few years time, so this technology will be commercialized. Okay, so this is also based on the range of size that you have in the water. Say, like for example, the bacteria, what are the size range, and what is the size range of the molecular size range of the membrane processes. So this, based on that, you can see that which, for example, if you have this many different types of composition in your wastewater, you have to see, okay, which membrane process is best. So you'll see that if you put reverse osmosis, of course, you can remove everything, but of course it's expensive as well. But if you use ultrafiltration, it can remove all the virus and many other color and those sort of things. Okay. And membrane process, you can use it for this ultrafiltration and microfiltration. Ultrafiltration, which is a porous membrane, they require pressure, but not as high pressure as the nanofiltration and reverse osmosis membrane. So usually nanofiltration and reverse osmosis membrane is very highly energy intensive because they have to operate at very high pressure. So what can happen is that in the process, if your water quality is not so good, then this RO and NF can foul, we call it membrane fouling. So it means all this deposit can happen, bacteria can grow, and then what will happen is the reverse osmosis membrane will fall, and then they have to clean it, and so there's a lot of energy will increase because when fouling happens, your water that's coming will be reduced, right? So or to get the same amount of water, you have to put more pressure. So in that way, you either you decrease the output, or to keep the same output, you have to spend more energy. So you don't want that to happen because it will be expensive for the treatment plant, right? So that's why we use microfiltration and ultrafiltration as a pre-treatment to make the water uh, quality better, improve, so that reverse osmosis and nanofiltration can target. For example, when you want to treat the seawater, okay, when you want to desalinate the seawater, you cannot directly apply the seawater to the reverse osmosis membrane. Otherwise, then within few hours, your membrane is damaged, or then your water will come out very less. So you have to put a lot of energy. So you want to, because the reverse osmosis and nanofiltration membranes are, our target is to just remove this divalent, monovalent ions and divalent ions. That's like the salt, just basically the dissolved salts that MF and UF cannot remove. These should be the only target. But if these other organics present in that will create a problem for RO membranes and nanofiltration membrane. So that's why we use MF and UF as a pre-treatment to remove all this the non dissolved suspended particles and macromolecules. So in that way, they use as a pre-treatment. So when you do that pre-treatment, then the RO and NF can work very, very efficiently. So in many seawater desalination plant and the wastewater recycling plant where they use reverse osmosis membranes, then they have either MF or UF as a pre-treatment in most cases. Okay. Yeah, there's a few terms, key terms that we use in membranes that you should be aware of. Okay, so in membrane filtration, we have two types of process. Whether you have dead end filtration or the cross flow filtration. So dead end filtration is, for example, so for example, this is the membrane. Okay, this is the membrane. So if the membrane is like, okay, I put the membrane here, okay, perpendicular to this is the feed water, that's the raw water that's coming, okay, for treatment. So if you put the membrane like this, then you filter the water like this through this one because of the pressure, and all this deposit will be here, the whatever is not removed, right? So this is a dead end. So whatever you filter, everything comes out, and whatever is not filtered, they just remain there. So, okay, which means there's no way to come out. So that's called dead end filtration. So this is very ineffective because what will happen is all the deposit will deposit will happen on the membrane surface, and within few minutes of filtration, your membrane will be completely choked. Okay, a thick layer of dirt will be formed. So membrane will no more. I have to push like very hard. Same thing, for example, if you have a syringe filter. Okay, if you have a syringe filter, initially the water will come very clean, very fast, but as the filter gets blocked, you'll have to press it hard to get the water, right? So same thing here, you have a dead end filtration, right? So that is not very efficient, but you don't have to have that kind of thing. Now what we do is, instead of dead end filtration, we have what we call cross flow filtration. Okay, cross flow filtration means, okay, cross flow filtration, you have a membrane, usually it is like this, okay, horizontal. Okay, I've just put it here inclined, but so the water will come here on the membrane, so water will pass through the membrane, right? And then whatever is not, whatever is rejected, whatever cannot pass through the membrane, like dirt and all suspended particles, they will come out as a dirty water. Okay, so whatever goes in, everything will not be filtered out. Okay, and the rest will come out as a reject. We call it, this is a concentrate or reject or a brine. So depending on, say for example, if it is seawater, and then all this will be a lot of high concentrated salt, so that we call it brine. Or if something that's rejected, we call it reject. Okay, so we have feed water which is coming in, we call it feed water for that feed that is coming in. That's the raw water that's to be treated. And the one that is filtered, we also in the high school you must have learned it as a filtrate. So but in usually in membrane process we call it permeate. Okay, permeate water, because it has permeated through the membrane. So whatever is not then we have also said reject. Now we have the flow rate of the inlet denoted by F. So QF is the flow rate that's coming in. CF is the concentration of the pollutant that's coming in. So it can be anything. It can be organics, concentrate organic matter, BOD, COD, or it may be salt concentration. So this is the CF, and CP is the concentration that is not filtered and then it's just going out with the water permeate. So because if you use microfiltration membrane, for example, not everything will be filtered out, right? So some will go through and most will be rejected. So now when you have this kind of membrane process, you can do the mass balance, because whatever goes in has to come out together, right? So whatever comes out here has to be total equal to whatever is going in, because there's nothing being accumulated here. So that's the way we do for mass balance. You can do volumetric mass balance and the mass balance of the pollutants. Okay, if you do the volumetric mass balance, so QF, okay, QF that's coming in should be equal to QP that's going out and QR that's going out. Okay, so these two. And the solid balance, the dissolved solid, suspended solid, whatever, the balance will be whatever comes in will be the flow rate multiplied by the concentration, right? So QFCF will be the mass that is coming in of the solute, and whatever the mass is permeating through the membrane will be QP into CP, and whatever is being rejected will be QR into CR. So that should be QFCF is equal to whatever is mass coming in is equal to whatever mass going out as a permeate and going as a reject. So that is the mass balance. Through that, then you can work out how much, if this is this much, you say for example if the water CP is this much, how much do we expect from here. Okay, all those things we can work out using this. Okay, so water flux is another very, very important parameter that we use in the membrane process. So it is defined as the volume of water, yeah, passing through a unit area of the membrane in a unit time. Okay, in 1 hour, for example, through 1 square meter of membrane, how much water will pass through. Okay, so that's called the water flux. Okay, so it's also in sometimes is a kind of throughput, that how much product you are getting, the throughput of the membrane process. So JW is equal to total volume water that is filtered within certain time through a membrane area of A. So if you do that, you will see that volume divided by time is nothing. So volume by time is the flow rate, right? How much volume of water that's going through in unit time, we call it flow rate, right? So this is flow rate is the QP, because this is how much you have produced the water, filtered water. So QP is the throughput water, so that's how much you have filtered. So QP by A, yeah, QP means the flow rate of the permeate divided by area of the membrane that you use. So that gives you the water flux. For example, if the water you're filtering is say 100 liters of water, okay, 100 liters of water in 1 hour. So okay, you got permeate 100 liters in just 1 hour. Okay, and if you have a membrane, total membrane area is, say for example, 10 square meter. Yeah, so through 10 square meter of membrane, you're able to get within 1 hour 100 liters of water. So that will be 100 liters divided by time is 1 hour, area is 10, so that means 100 by 10, that gives you 10 liters of water in through 1 square meter in 1 hour. So that's called, we call it liters per meter square per hour, or LMH, liters square per meter square per hour, right? Liter per meter square per hour. Or we usually denote by LMH, liters per meter square per hour. But you can use different, in the US, for example, they used gallons per foot per day. Also is another unit for the water flux, okay? So any questions so far? Okay. So there are other terms, the rejection rate. So rejection rate by the definition is how much is being rejected. For example, rejection means we're not talking about the water, we're talking about the pollutants, okay? It can be suspended solid, organic matter, BOD, COD, or, salt concentration. So how much is rejected means how much salt is rejected, percentage is rejected, okay? So if CF is the concentration in the feed, that original one, raw water, and then CP is the one that is in the permit, right? So permit is you're not able to filter. So the CP is there because the membrane is not able to filter everything, right? So that's why some concentration still pass through the membrane. So if you subtract CF minus CP and give the ratio to the original one, that gives you the ratio that's called the rejection rate, okay? How much percentage of the pollutant that's coming in is rejected. So that's called rejection rate. And you can give CF minus CP by CF into 100. So that gives you rejection rate. So you'll, in the membrane process, first people will ask is, people who are working on membrane, they'll ask is what is the flux and what is the rejection rate, how much is rejected? Because that's important, because if rejection rate is very low, that means this membrane is letting it pass through many things. So it's not filtering it, it's not removing it. So that means low rejection means low quality, yeah, the water you will get. So high rejection means that you get better quality of water. Okay, so we used other instead rejected means that's the what we'll get in the brine or concentrate here. But sometimes you walk through the other way, you also measure in terms of how much it passed through. Okay, so that's called transmission, how much it's transmitted. So if, say for example, if 50%, if 80% is rejected, then out of 100, yeah, 20% is passed through. So that's transmission. So that's give you the transmission percentage. So 1 minus rejection rate gives you the transmission rate. But transmission rate is hardly used in membrane industry. So it's usually the rejection that is important. And feed recovery rate is another important thing for operation. So you have, say, for example, as I said, this is a closed flow mode. Whatever you feed here, whatever the amount of water that you send in, raw water that you send in here, everything cannot, 100% cannot become a clean water. Yeah, someone will have to be rejected because they cannot filter everything together. And so this, how much you filter out of how much you put in, that's called the recovery rate, feed recovery rate, okay? So feed recovery rate is equal to QP, how much you have filtered through, divided how much you have feed in. So that gives you the recovery rate. So usually in the, let's say, microfiltration and the ultrafiltration membrane, the recovery rates are quite high. Say like 90%, 95%, 80% they can operate. But for nanofiltration and reverse osmosis membrane, they say, for example, seawater reverse osmosis membrane, around 50%, 45 to 50% is only the optimum. If you go beyond that, you have to have a lot of energy and a lot of fouling issues. There are a lot of, because when you operate at very high pressure, the water all the water will go through, right? And more salt will be rejected. When more salt is rejected, and then some of the salt may not be soluble. So if the solubility of salt is decreasing and then not very high, then, like for example, like a gypsum, calcium sulfate. Calcium sulfate solubility is very low. So if your seawater has a calcium and sulfate together, then the calcium and sulfate, as they are rejected by this RO membrane, they will come on the surface and then easily nucleate and then form calcium sulfate precipitate. And then in all this scaling will be formed on the membrane, and the water membrane will be blocked and choked. So you have to have a cleaning process. So that's how the fouling has to be and the membrane has to operate it at a certain feed recovery rate, not very high. So there are some call it critical flux, where critical flux and critical this recovery rate will be quite dependent, because if you operate at high recovery rate, your flux will be higher. Okay, so when your flux is higher, more deposit will happen on the membrane, and then membrane will be fouled quickly. So there's an optimum condition that you have to operate. In that, your fouling rate will be low, and then in that way, the cleaning, the duration is reduced. So this is the different membrane modules, because the idea behind membrane is also to make it very, very, very compact. Sand filtration, you got very large surface area, because they depend on the surface area to filter it. So if you want to have more filtration, high amount of water filtering through the treatment plant, sand filtration, you require a very large area. But the beauty with this membrane is because they are very thin, less than 1 millimeter. So you can see from the sheet here. Remember, this is the membrane from the manufacturing, the flat sheet membrane rolls. So these flat sheet membranes are rolled in, then made into the modules. Okay, this one we call it spiral one model. So you have this kind of spiral one model. This membrane in between, they have spacers where they provide a space for water to run through, and this called feed spacers. And then in that way, they are spirally wound, and then there's one side of the membrane is the feed water that goes through, and the other side of the membrane is the clean water that flows through. So they will fall in a very circular way, and then from the permeate, the clean water will come out from here, and the feed water, for example, feed water will go through this from the side. So in that way, inside there's a tube from where the filtered permeate water comes in. And these membrane modules are then stacked, pushed in within this, call it housing. Okay, these are called housing. So there's sometimes one housing can fit up to like 7, 8 modules inside. So then fit it in series, and these are called also pressure vessel membrane. So inside this, because they have to withstand high pressure, so inside this housing, this membrane, let's say the modules will be kept, and they will connect it in series. And then when you feed the water, raw water, under high pressure, and then the water will pass through the membrane, and at the end, the cumulative, all from first module water goes in, second module comes, and finally they get water from all these elements by the end of the housing. So in that way, you have stacks and stacks and thousands of hundreds and hundreds of this module stacks. So in that way, you get very, very compact treatment plant. So if you will be amazed if you visit one day, happen to visit Sydney desalination plant. If you have time, in the future, you just visit it. It's amazing that you have seen like stacks and extend hundreds and hundreds of stacks of this kind of modules put in there. So because in one module you have to have a lot of, because otherwise you can in one module has certain capacity to produce. So maybe 1 liter, say one module will produce around 100 liters in 1 hour or something like that, right? So but then you have to have a lot to produce enough water. Okay, so this is called very spiral one module. There's a YouTube link given here how this membrane is made by Dow Jones. So just look at that, and then not Dow Jones, sorry. Dow Jones is the share, that is the market there. Is Dow is a company, the membrane manufacturing company. So there is an industry that they supply this kind of membrane modules. Okay, so you see that here they have a lot of high pressure membrane pumps. So because they have to be, especially if it is a reverse osmosis membrane, they require very high pressure. So high pressure means this kind of, one of the most expensive cost, the highest cost component of the desalination plant is the pumps. Some of the, say for example, in the Sydney Sydney desalination plant, they have huge pump. I think there are 4 or 5 pumps. One pump is, like something like $50 million or $100 million. Huge. It's because it can generate up to like 1,000, so 70, 80, 90, up to 100 bars of very high pressure. So this is a flat sheet membrane, okay? So they are spirally wound. And then you have also other form of membrane like a hollow fiber. Yeah. So flat sheet also is very compact. You can have, say, if this membrane is, say, for example, if it is a 4-inch membrane, we call it 40-40 module, okay? It's a 4-inch membrane and 40 inches long. So that's at 1 meter, I think. And that will give you around 10 square meter of membrane, 10 square meter of membrane within very small compact area. So 10 square meter membrane. No way in the sand filtration you can achieve. Sand filtration, if you want 10 square meter, means you need like how much? 10, 5 length long surface area by 2, right? So you have 5 meters by 2 meters of space in the plant area, then you get 10 square meter. But this membrane, within that small area, you can have a 10 square meter. So which means if you have, in this housing, there are 10 modules, means 10 in 10 days, you can, in one module, you can have 100 square meter, okay? 100 square meter of membrane area. So imagine if 1 square meter is giving you, say, 10 liters of water in 1 hour. So in 1 hour, 10 into 10, right? 10 into 100, sorry. So this will give you around 1,000 liters of water. So that earlier I said was, I think, the wrong number. But if you get 10 liters of water per hour, so we said 10 LMH is the flux, okay? Then one module has 100 square meters, so 100 into 10, you'll get 1,000 liters of water from just one tube, okay, one housing here. So that's how it is stacked up to get the millions of liters of water every day. So next one is the hollow fiber. So hollow fiber is even more compact. We can have a dense water. So for example, if for the same module, okay, 40-40 module, if you have, I think probably it will be maybe twice or even more than that, depending on the size of the hollow fiber. If the hollow fiber size is still, if the diameter of this hollow fiber is still is even smaller, then you can even increase the the area, total area. So sometimes maybe in this one you can have around 30-40 square meter of membrane area instead of just 10 in the spiral one. Because in spiral one you have to have a spacer in between. So in that way it becomes a little bit thicker. So if you look at this, the cross section here, you have seated thousands and thousands of hollow fiber membrane staying here. And in that way they become very, very compact, okay? So these are the hollow fiber membrane modules. And hollow fiber membrane module is used either on this type of housing where the water flows through, especially from the outside, and the raw water from flows outside, and the clean water comes inside the module, okay, inside the fiber. So here, if you can have this kind of housing, and the raw water flows outside of the fiber, and then you get from the other side. One side is clean water and the other side is the reject one, okay? But also you can just directly immerse this hollow fiber inside. You don't have to have a housing, but you can directly immerse in the water. So that's how we call it membrane bioreactor. We use that. In the membrane bioreactor, we have this kind of hollow fiber membrane which is already exposed, okay? And then we just put this one inside the bioreactor of the wastewater treatment plant. The activated sludge process, you have the aerated bioreactor, and then you just put this membrane inside, and then but here you cannot put the pressure because there's no way to put pressure because your membrane is exposed. So only you can suck suck it. So you have this will be sucked through using a vacuum on the other side. Okay, so all the water will be sucked in, and then it will be filtered. So that's how the membrane, submerged membrane, we call it submerged membrane or the immersed membrane. Okay, so this we will cover a little more later in the chapter. So as I said, membrane fouling is one of the very much challenging problem, very problematic in the membrane industry. It's the accumulation of all this dirt. So look at see the if you put the membrane inside the bioreactor, of course they will deposit all the sludge here. Even the the spiral one. Look at this. If your membrane, the feed water that's going in is not clearly treated and removed from the organics, and these membranes will make the dirt that is in the membrane will not only deposit on the membrane surface, but they will let the bacteria grow. So this bacteria will grow, then biofouling will happen, because this when the bacteria grows, a biofilm will be formed on the membrane surface. So imagine if you put if you keep some any object in the water, immersed in water for overnight or 2 days, or 2 night or few days, and when you take it out and then you try to peel that, then you'll feel like the slimy thing. So that slimy thing is because the bacteria goes inside, the bacteria stay there, and the bacteria will release some kind of enzymes or some kind of discharge. So that very sticky thing, that sticky thing results like a glue, and then more organics, more dirt will exchange in, and then become worse and worse. And then after a few days, nothing will come out of the membrane. So if you open the membrane, you'll see that this membrane is really foul. You can see if you try to look at the microscope, you will see that there's so much cake layer formed inside. Okay? This is one of the biggest challenges of the membrane. So they can even block the pores, right, like this, and then they won't let the water pass through. So when you do that, then of course you have to either push the membrane so hard, then you have to clean the membrane. This is the time taken, and you have to use chemicals to clean. There are three types of fouling here, mainly inorganic fouling, biofouling, and organic fouling. Organic fouling, is the name suggests, the organic matter that's biologically degradable. All these things can and then become food for the bacteria, and then even grow worse. Inorganic membrane is like scaling I was talking about, like gypsum and sometimes even silt, or can come, and then the colloidal particles can come and then cause the fouling. Biofouling, of course, is the bacterial impact. So all this can result in significant increase the energy, increase in the operation cost, and also plant downtime. And so that's how we want to avoid. But yeah, so there are some ways, strategies how we can operate that and reduce the. We can't really eliminate the membrane. Fouling, because it's a very uh, it's naturally happening, because when you remove something that will you cannot when you filter something, that has to be on the surface to when you filter. So that causes any problem. Yeah. Anyway. So there are physical cleaning, after, say, like for example, if it's the microfiltration, they are designed to say, okay, the cycles of cleaning and operation. They will operate for around 30 minutes, and then they will stop, and then they will backwash for maybe 2 minutes or so, and then again. So there's a continuous cycle of cleaning and backwashing, cleaning, chemical cleaning, physical cleaning. Usually it's physical cleaning, and chemical cleaning is like maybe once a week or once a day, only once a day, or maybe sometimes if it's other membranes like reverse osmosis membrane is once a month, or in once a 6 months, something like that. Okay, so there's a chemical cleaning, physical cleaning, and also disinfection. So because in order to prevent biofouling, you have to kill bacteria, right? If bacteria is killed, then you biofouling will not happen. So disinfection can be put before that. But there is also a problem with reverse osmosis membrane. If you put chlorine in the feed water, and then if there's a residual chlorine, this chlorine can damage the membrane also, RO membrane. So that's why we don't usually chlorine for disinfection before the RO membrane. So there are some other disinfectant that you can use. So how to prevent fouling? So these are like chemical cleaning, physical cleaning, and disinfection are but once your membranes are already fouled, but you can prevent, reduce fouling. So of course, we said cross flow operation instead of dead. That's what most of the operations are in a cross flow mode, because dead infiltration is really more prone to fouling. And as I said, is a critical flux. If you operate at a higher flux, then higher deposition happen and higher fouling rate. So you have to have a certain optimum, a critical. If you operate below that critical flux, then membrane can operate for a very long time without having to clean. But if you operate a very high flux, then you get initially a lot of water, but your operation time will be significantly reduced. Then severe membrane fouling. So that's how so one of the strategies to operate at a lower than critical flux. Disinfection also try to use some biocidal to prevent biofouling. So instead of chlorine disinfection, some biocides are used to prevent biofouling. And pre-treatment of water. So you have to have a very high quality pre-treatment. So remember earlier I said microfiltration and ultrafiltration, they can be used as a pre-treatment before sending it for the reverse osmosis treatment plant. So that also really significantly reduced the fouling on the RO membrane. And also you can optimize cleaning frequency, membrane cleaning frequency. So these are some of the system optimization that you can do. Okay, so we are now 10:30. So probably maybe we should have a little bit of break. Maybe it's 10:37. How about we join at the resume at 10:47 after 10 minutes? Okay, and then we'll do some basic membrane calculation, and after that, then we will go for the next chapter, the last session. Okay, is that fine?
Okay.
Okay, I'll see you at after 10 minutes then, 10:47. Okay, let's start now. Welcome back. Okay, so let's start with this some basic calculation, membrane calculation. The question here is a membrane unit has an effective membrane area of 20 square meters. Say if this is the membrane, the area, total area we have, say it may be square or one or whatever. So we have an effective membrane area of around 20 square meter. Okay? It is operated under a closed flow condition 8.8 bar. Okay, 0.8 bar. So that's less than 1 bar. So we assume that this is a microfiltration membrane. With a feed flow rate of 50,000 liters per day. Okay, the flow rate here is 50,000 liters per day, and producing a permeate or flow rate of 45,000 liters per day. So you're feeding in the raw water is 50,000 liters per day, and the product that you're getting is 45,000 liters per day. So the feed water has a turbidity of 30 NTU. Okay, is quite turbid here. Okay, while the turbidity of the permeate was measured to be 1 NTU. Okay, so you're asked to calculate the following from the provided information. One is the water flux. What is the water flux for this operation under in terms of liters per meter square per hour? What is a specific water flux? So water flux and a specific flux was a little bit, different with addition of pressure here. Why water flux sometimes can be misleading, because if you operate it, because the water flux that is coming from the membrane depends on the pressure. Okay, depending on the pressure also. Okay, there are other parameters, of course. You know how much organic content is there, what's the pore size, everything can impact. But one thing that operation impact is the pressure. Okay, so if you apply higher pressure, you'll get more water flux, right? So that means, so if you just say that, okay, I have a membrane which the water flux is 10 liters per meter square per hour, 10 LMH, and others say, oh, mine is 20 LMH. Then how is, oh, 20 LMH is better? How? Because that means 20 LMH maybe because he operated at high pressure, right? So the other guy may have operated at say 2 bars. Okay, he applied at 2 bar pressure and then he got the water flux of 20 LMH. The other guy applied only at 1 bar and he got 10 LMH. But if you look at, they are almost same, right? Because the other guy is they're applying a 2 bar. So when you bring back to the unit pressure, then yeah, that's called specific water flux. Okay, so we have a specific water flux. You have to, in terms of liter per LMH per bar. Recovery rate, that's called feed recovery rate, and turbidity removal or rejection rate. So this is what we have to calculate. Okay, so from the given. So given here, the QF is 50,000 liters per day, QP is 45,000 liters per day, and area of the membrane is 30 square meter. Concentration of the feed is 30 NTU, concentration of permeate 1 NTU, and delta P here is the pressure difference that you're applying is 0.8 bar. Okay, so if you look at this, so that's how you have to do the formula to calculate. So this is what going in, going out as a permeate, and then going out as a reject. So this is how you can do the calculation here. Now we first are asked to find the water flux. So let's JW. So JW is given by the permeate flow rate divided by area. Okay. So QP is already given as 45,000 liters per day. So now you have to be careful with the units here, because it's a unit is liters per day, whereas water flux you are asked to find in liters per meter square per hour. Okay, per hour. So now you have to convert into the liters per day. Okay, per hour. Okay, so let's replace this one in 45,000 liters per day. Area is 20 square meter, so you get 2,250 liters per meter square per day. Okay, so in 1 liter, in 1 hour, 1 day, through 1 square meter of membrane, you get 2,250 liters. Okay, in 1 day. But how much you get in 1 hour? So divided by 24, because 1 day is 24 hours. So you'll get divided by this one will give you 93.75 liters per meter square per hour. Okay, so in 1 hour you'll get 93.75 liters from 1 square meter of membrane. So that's called the water flux. Okay, any question on this one? But this is very simple one. Yeah. Okay, now specific water flux will be JW. Okay, so this is the water flux per unit pressure. So pressure applied is 0.8. So you divide that water flux JW by the pressure is applied, so 0.8 bar. So you get 117.2 liter per meter square per bar. Okay, so which means if you apply, just now you apply only 0.8 bar. Okay, but if you, what it says from this data is that if you apply 1 bar, okay, you will get 117.2 liters of water in 1 hour through 1 square meter of membrane area. Okay, and the recovery rate here is the formula for the recovery rate is how much you produce here per minute. Okay, QP divided by how much you're feeding in. Okay, so the product, the flow rate divided by product feed in. Okay, not product, the raw flow in. Okay, so that gives you QP by QF. So that gives you 45,000 liters per day divided by 50,000 liters per day into 100. That gives you 90% recovery rate. So the under this operation, if you are feeding in 50,000 meter cube per day, and you're getting product only 45,000 per day, so that means your recovery rate that this membrane operated is 90%. Okay, 90% recovery rate. And turbidity removal rate or the rejection rate. So you know rejection rate is equal to the concentration inlet concentration of the feed concentration minus the product concentration. So if you minus that, that's what is rejected, right? So divided by CF is into 100. This gives you 96.7%. So that means this membrane is able to reject 96.7% of the turbidity, okay, NTU. Now I can ask other question. Can instead of CP, can you use CR? CR by CF and then CA, okay? Can you get the same? So yeah, but you can't, you won't get that because the concentration has changed a little bit here because so in that way there is no value that you can find from CR. I don't think you can get from CR by let me check. Okay, that's what where is it? My calculator here. Can someone do the calculation if you find okay? Of course we don't have a CR here, so that's the problem. Because CR, you will have to do the mass calculation to see what will be the CR. Okay, mass balance calculation. So for example, if I go back here, remember the mass balance calculation. Okay, so here this one, if you want to see calculate what is the concentration of CR, okay, what is the concentration of CR that's being rejected here, you can do this mass balance to do the calculation. So CR will be equal to CF QF into CF minus, you take that side, so this will QP CP and then divided by QR. So that will give you the concentration of CR. So in that way you can also check, but I think the rejection rate will be different. So it's not, that's not applicable, okay? Okay. So rejection rate is 96.7%. So we did the basic calculation. So yeah, we did recovery rate, turbidity rate. So this is what the question is asking. Okay, so you just practice at home yourself. So
Low
because
charge.
what is that? Low charge? Oh, I see. Okay. Sorry. My soundbox charge is low, so that's why it's saying low charge. I'll just put it off. Okay, that's fine. Okay, so can someone say something because I need to see that my sound is working because my battery is run out here, soundbox.
Yeah, we can hear you, Professor.
Oh, can't hear anything. Amit, can you say something?
Yeah, we can hear you,
Okay.
Professor.
Okay. Great. That's fine. Thank you. Okay, so let's do another set of calculations here. Okay. A new water treatment plant of 100 mld. So 100 mld means 100 million liters per day, okay, or megaliters per day, you can say million liters or megaliters per day. Capacity is to be built using a hollow fiber membrane, okay, microfiltration membrane, hollow fiber. So the nominal size of the pore is zero 0.1 micrometer. The water flux of the microfiltration membrane was tested in the lab using the real water sample and showed an average water flux of 50 liters per meter square per hour, okay, LMH, at 0.5 bar, okay, applied pressure at a recovery rate of 98%, okay. So now we are going back the other way around because earlier we tried to work out on the, the recovery rate, but now recovery rate is given, flux is given, okay, and so the treatment capacity is given, so how much product you want, okay. Each hollow fiber module has a membrane area of 100 square meter, okay. One hollow fiber membrane like this, say for example, like one hollow fiber membrane, one module has 100 square meter. So now you have to calculate the following: the total membrane area required by the water treatment plant. So how much the area is required, okay, because flux is given. So now you can find out how much membrane is required because you're asked. So this is the scenario where you're asked to design the membrane treatment plant, okay, membrane process for the water treatment plant. So then you have to find how much area or how much membrane module is required. So first you have to, okay, the plant capacity is given. Okay, you have a client here. Okay, I want to say somebody comes up and said, okay, well, Anmar, okay, I want to design this. I want you to design my water treatment plant. My requirement is that I need 100 million liters of water per day. What how much will it cost? How much membrane do I require? Area do I require? So that's all you have to find out, right? So now you go to the membrane manufacturing company, and manufacturing company has given you some information, okay, but now you have to also determine yourself. Okay, you brought some sample from the water membrane company, and then you tested yourself using the same water that you're going to filter, and then when you do that, you found that water flux that you get in 1 hour from through using 1 square meter is that you get 50 liters of water per meter square per hour, okay, at 0.5 bar, okay. When you apply at 0.5 bar, you get 50 liters, but if you apply 50, say 1 bar, I think you will get double, right? Say if it is linear, so 100 liters per meter square per hour per bar, right? Now, so, and also the membrane company says that, okay, we have very compact module. One module of hollow fiber, you can have up to 100 square meter. Okay, that's very good. Now, so you can say, okay, the rejection rate, the recovery rate we can apply is 98%. So which means if you apply 100 meter or 100 meter cube of water per day inside, you can get 98% as a permeate product. Only 2% is reject, okay? So this information is given. Now you have to calculate how much membrane area is required, how much membrane module is required, and what's the flow rate you have to put in inside, because output is given, how much you have to fit in is not given. So that's what you have to find out, how much water has to, because this is important, because it will depend, this will dictate how much actually, if you pre-treatment is required, because if you have membrane filtration and before that you have to have some other kind of filtration or some kind of treatment, then you need that treatment process capacity to provide enough water for your thing. Yeah. So the total water that you want is not 100 meters square, because 100 mld, because 100 mld is the one that you want as a treated water. So usually what you feed in should be more than 100 meter, because some will be rejected. So this is how it's one of the problem is. Let's do the calculation here. Okay, the informations are provided here. Okay, so the total membrane area required will be, okay, so the just earlier we used JW is equal to QP divided by area of the membrane, right? But now you just the area of the membrane will be equal to Q by JW, and both are given. So this will be 100 million liters per day. Okay, 100 million is 10 to the power 6 liters per day divided by 50 liters per meter square per hour. So I'm putting the unit here because they are in different unit. So if you walk directly, just divide by 1000 and then do it, then you'll be in problem, because your units are not, the answer will be wrong. So liters per day, liters per meter square per hour. Okay, now you have this liter is liter same here, there is no meter square here. The hour and day are different unit of time. Okay, so you have to convert this one, either you have to convert this one into day or this one into hours, right? So let's convert this one into hours. So when you convert this one into hours, so one day is 24 hours, so you divide this one by 24 hours and the 50 remains same, then you will get the total membrane area required to filter 100 mld of clean water is 83,333 square meter. Okay, this is based on the water flux that you obtain by testing. Okay, so this is the 83,000 square meter required. Now this is the total membrane area required, but each module is like each one module is 100 square meter. So how many modules you require? So that will give you total number of modules required is equal to total membrane area required, which is 83,000. Then the membrane area of each membrane module is 100 square meter. So that means you require around 833 number of modules. Okay. So 833 number of modules you require to treat this much amount of water. Now, what's the feed flow rate that you require? Because the recovery rate is given that, okay, you operate at 98% recovery rate. So which means it's not 100% becoming permanent, right? So your reject, some are becoming reject. So 2% is becoming reject. So that's why if you work out here, you have this formula, recovery rate is equal to QP by QF. So we don't know QF. So that's what we want to find, QF. QP is given as 1000, okay? Recovery rate is given as 98%. So you substitute that one, you'll get QF is equal to 100 by 98. So that means 102.04 mld per day. So your feed water flow rate has to be 102 in order to get 100 mld of the permit water. Okay, so the QF should be 102.04 mld. Now you ought to find what is the concentrate flow, what's the rejection flow rate, how much will be rejected, how much volume will be the brine, okay, brine volume. So okay, here, so you put this much, you're putting 102 here, getting 100 product here, so that means definitely the brine will be the difference between these two, right? So that is the brine flow rate. It's just a very simple one. Okay, so brine flow rate QR will be equal to 102.04 minus 100, that gives you 2.04. So that will be the brine coming as a reject from the treatment plant. Okay, any questions so far on this? This is very simple calculation, of course. So this calculation used to be there because you used to have a exam before for this particular subject, but later on we removed the exam. So, but of course, these are basic ones. Then if somewhere in during your career, maybe that you will have to do this calculation one day, like no. This can applicable not only just large membrane treatment plant, even if you want to have if you want to install some membrane filter at home, for household for your own consumption. Maybe this small this brief calculation is important. Okay. Why is surface treatment plant is coming here? Okay, so now let's how the membrane really helps in optimizing the space. So membrane, as I said, membrane is very thin, whereas usually the sand filter is very large. And so because of that thin, very thin and very compact, they can be squeezed within a very small footprint, okay, small size area. So that's the advantage. How we can do that? So this is how the membrane can be very useful. So for example, you have a surface water treatment plant. This is a conventional treatment plant that we earlier discussed. You have screen bar, you have chemical mixing here, flocculation, then you have sedimentation, then after sedimentation, you have filtration, and then it goes to the disinfection and then supply, right? But if you replace this one with a membrane, okay, then you can save a lot. So here is you can still keep this screen bar and all the grid chamber. Then after that, it straight away goes to membrane filter, okay? And then the membrane filter directly gets. So which means how many process it substitute. So from here, it directly goes to the permeate tank. So this is the permeate tank, okay? So which means, look at here, it replaces mixing here, flash mixer, flocculation tank, sedimentation tank, and filtration tank. So in fact, it's three major processes, because chemical mixer is not very large space required, but flocculation is quite significant, and sedimentation, as you know, is very significant, and even filtration. So 1, 2, 3 major process it can replace by just one membrane. So that is the beauty of the membrane process, okay? So if you don't have to see, imagine this one, so within the space of the probably not even the space required for flocculation here, tank, you can have just the membrane filter. Okay, in that way you save the whole space for sedimentation and filtration. Okay, and by sedimentation filtration is the very large membrane area. If you look at the water treatment plant or wastewater treatment plant, the diagram, the process diagram, and also from the space, like for example, in the satellite pictures, if you see some of the wastewater treatment plant, water treatment plant, you see large tank, circular tank. Those tanks are circular tanks are the flocculation tank and the sedimentation tanks. So they're quite large, so literally require a lot of space. Some are like 150 meters of the the diameter. So this membrane can simply replace those kind of area required for the conventional treatment plant. Okay, that's the beauty of the membrane process. Of course, the cost of the membrane is still high when you compare with the conventional treatment plant. If you have a space where the land price is not significant, yeah, of course, then conventional treatment is still could be still cost effective. But if it's a space, if your treatment plant is to be located at a place where the land prices are quite high, so then yeah, this membrane can be very, very cost effective. Okay, so membrane direct filtration here, okay, even you didn't need other things. So usually membrane can be used as to make for disinfection, also as make it the potable water directly, just using a bit of pre-screen and direct microfiltration. And then with the microfiltration, you don't need other things. So for example, if the water quality is a little bad and then you're not able to remove this bacteria and there's some bad virus still there, so you can use this kind of ultrafiltration membrane. So for example, if you want to remove cyst or cyst bacteria, and to remove that, you can have microfiltration or ultrafiltration. They will remove almost actually 100%, but to have some kind of double assurance, okay, security, then you can put ultraviolet rays after that, UV disinfection, ozone disinfection, or even some more chlorine or chloramines or the chlorine dioxide, because they are not very strong required for before distribution. So these are some of the very simple one one process, two process, just three process that you can have a very treatment plant. Okay, even you can have this kind of very simple one at home. Okay, if you're not very confident with your water that you get from the supplies, of course here in water is in Sydney is safe, but if it's in other countries like some countries, you may still get very poor quality water, and people don't drink without boiling the water. So in this case, if you want to have more secure water at home, yeah, you can put this kind of very simple home, because the small unit process are available nowadays. The membrane process together with UV. Ozone is a bit challenging because their ozone mechanism for treatment is a bit different. UV is quite straightforward. You just put the UV lamp and then let the water pass through the UV lamp, and then it will be disinfected. And chlorine also, like sometimes nowadays even you get this chloramine and then this chlorine tablet. You just put in there and then water will be disinfected. So in that way you get very safe, clean water at home. Okay, so that ends the membrane processes. So the third comes the block C, 2C, which is the wastewater treatment process. So we will do a little bit on the conventional activated sludge process and the MBR, membrane bioreactor. So why wastewater is actually much more complex compared to what the surface water, as you know, because what wastewater, what surface water has, the wastewater has, and more than that. So the most important thing that you have, major thing that you have, is the fecal matter, the human waste that you add in from the toilet and also from the kitchen, and also the chemicals that you use at home. You use a lot of detergents to clean. You use dishwashing agents. You use the soaps or the detergents, laundry detergents to use, and on the you use some more softening, some disinfectant you use, and a lot of chemical. Even sometimes you use in the toilet to to remove the odor. You use some chemicals. So a lot of chemicals that you use at household. Sometimes you throw just some chemicals that you don't use at waste at home. So all these chemicals can contain in the wastewater, which is very complex. Okay. So as I said earlier, the wastewater treatment can be treated using three major fundamental processes: physical, chemical, and biological process. Okay. Because and then the most important thing about is the wastewater for the domestic is it contains very high organic matter. And also it has a lot of microorganisms. So fecal matter has a lot of fecal coliform microorganisms. So that needs to be removed. So our target for wastewater treatment is to remove basically the organics and the microorganisms. So some industry waste, sometimes trade waste also can be mixed with the domestic wastewater, and it can contain some other the wastewater, some chemicals or some other composition that is not from the household. So it can be from the commercial also. For example, if the sewage is coming from both the domestic and also from the commercial establishments, like maybe the hotels, restaurants, and all. Yeah, they may also use different some kinds of chemicals, and all this can become part of the wastewater. So mostly we will be talking here about the biological process. And so biological process, of course, is based on the nature, that we mimic the process that's happening in the nature. And microorganism, which is mainly the bacteria, is the most important. They play a very critical role in the wastewater treatment process. And in nature, it happens a very passive way. Okay, in nature, the biological process happens in a very passive way. So, for example, if you leave the water, wastewater in the open and store in the pond, for example, so nature will treat it because bacteria will eat, and but it takes time. So because the process is very passive, it takes its own time to do the treatment. But you don't have that luxury of time in the industrial process, right? Like in the wastewater treatment plant, you cannot wait for nature to slowly do its own course. You have to accelerate it, right? So that's what we make the active. Okay, so that's what the treatment we're activating the treatment process. So we're accelerating by controlling the environment which the organisms grow. So as you people studied the how this the process is being happening in what say nature, and then they try to apply that, and then in the process you try to see how we can accelerate. So what are the parameters, what are the conditions, environmental conditions that really helps in accelerating the biological activities. So that's how we try to control in the wastewater treatment plant. So the role of the microorganism include removal or decomposition of the carbonaceous BOD. Yeah, so the one of the major role of the organism is to eat and remove and decompose the organic matter, because as I said, organic matter is the major component in the wastewater. Okay, so they can only remove those that are biologically degradable. So that's why we say BOD, biologically degradable organics. They in the presence of oxygen, they can be removed. Okay, decomposed, because the bacteria use that carbon organics as a source of the food for them to live. They use that and then they multiply to cell multiplication. So when they do the cell multiplication, they need energy, and they get energy from the organics. Okay, and the other role is that they coagulation and flocculation of suspended. So how it happens is the bacteria, as they eat organics, they will produce discharge, this slimy thing. They would say the slimy that we call it EPS, the what is that? It's not coming. So EPS. So says polymeric substance is some polymeric substance that's like a glue, sticky thing that in the bacteria usually make. Like earlier, I was giving example. If you put a spoon in the water and keep it for a few days, when you take out the spoon, you feel the slimy thing, right? It's because the bacteria lives there, grows there, and then they discharge it. So that becomes sticky thing, and that sticky things really helps in the wastewater treatment plant. So that glue will act as a glue will stick and agglomerate and make more the suspended particles flocculate and become coagulate and become large and large particles. So in all these fine suspended particles, they become larger particles, so which is good so that you can settle and then be removed, because what ultimately we want is all these particles agglomerating. If whatever is eaten by bacteria you eat, and then whatever is not eaten, they become heavier and settle at the bottom, and they can be separated. So that's the coagulation and flocculation plays a very important role along with microorganisms in the wastewater treatment plant. And stabilization of organic matter is another one. So organic matter, so what happens? So what's the problem when if you release the wastewater just simply like that? It's the smell that's the problem, right? So what that smell is, there are many things. One thing, organic matter will rot, right? And only fecal matter is already smelly, right? Because there are a lot of organics there, and because digestion happens inside, it's already smelly. But if you store it for some time, then it will be more smelly because microorganisms will act it, and then so that's why the microorganisms play in stabilizing that kind of organic matter. So instead of becoming a very that will give you a foul smell, but this will give you a less smell and more stabilized form of organic matter. So this called chemoheterotropic organisms are mainly responsible for biological processes. Okay, so you can see what sort of organism this is referred to. So basically, these are different types. So many different types of microorganisms are there: bacteria, fungi, right? So there are certain species which are very good in just removing the BOD. Some are very good in removing the nitrogen from the. So there are different species, and even for same species, for say for example, those removing or nitrifying bacteria. There are so many different species of nitrifying bacteria, different types of denitrifying bacteria. So so thousands and millions of species are there. So everything plays a very important role. So what are the requirements for the microbial growth? So definitely one is the energy source that is provided by the BOD and COD, mainly the BOD, and it's because they as an actor, as a source of carbon for their growth, cell growth, because when the cell multiplies, they need carbon, right? Because cell is made of carbon and other fluids, right? So nutrients is required also, of course. And all this major and micronutrients are needed, like nitrogen, phosphorus, potassium, calcium, magnesium, like we need. Same thing the cells need, because they are also like proteins. We are also made of proteins, and they're also made of proteins and carbon, right? So of course you have said a lot of different types of biological processes. You can see from this textbook by Shobanagas, and you can have so many different types of biological process. Aerobic process, that process you activate using by providing a lot of oxygen. Anaerobic process is the process where you don't provide oxygen, but the bacteria will, in the absence of oxygen, they will try to decompose the organic matter, and the process convert into methane. So that's also one thing that very important role, and it's very smelly. So if you see a carcass that's being rotten and then inside, so that's because of anaerobic process. The what's it happening. The anaerobic process is also associated with release of hydrogen sulfide. Okay, hydrogen sulfide is the rotten egg smell, right? So that's how we can differentiate between aerobic and anaerobic through the smell also. Of course, aerobic process also smell, but not as strong as the anaerobic process. And there's another faculty process where is a combination of the aerobic and the anaerobic process. On the surface you have aerobic process, and below you have a anaerobic process. In between the mixture of both two. So that's, we call it the facultative process. So usually this is found in the large waste stabilization pond. In some countries, you may see that the conventional treatment plant, you have very compact treatment plant. You activated everything in a controlled environment. But there also we use a natural process, like a very large pond where you store. So that we are not really controlling the environment. We're just retaining the water enough so that they can be treated so naturally. So that's the passive and the active process. Okay. So in the passive process, this facultative process is quite important. Anox is another one where you have biological degradation of organics, and then it happens in the absence of oxygen. There is no oxygen, but there is some species of bacteria, we call it denitrifying bacteria. They are able to use the nitrate, because nitrate, NO3, has oxygen, NO3. So they have the capability to split nitrate and take out oxygen from the nitrate. So they use that oxygen for the synthesis of the organics, and then for the decomposition of organic, because they have to oxidize and then use that organics to as a food, and then for cell multiplication, right? So in the process, the nitrogen is released as a nitrogen gas. So in this anoxic process, very important in reducing the nitrogen, removing the nitrogen from the wastewater, and meet the total nitrogen standard. Okay. Nitrification is the process of converting ammonia nitrogen into nitrate nitrogen. Okay, ammonia, as you know, is ammonia. NH3 is a gas, and it is smelly. For example, you have a urine, right? Urine, when you pee, your urine is usually initially is made of urea, mostly urea, and other, of course, salt is there. But urea will, with the time, they will hydrolyze and then convert it into ammonia. Okay, so ammonia is the one that gives you a pungent smell. So urine, after the old urine will really smell pungent. Yeah, so that pungent smell is because of the ammonia. So that ammonia in water can be toxic, and also is smelly, right? So that ammonia has to be converted into nitrate to make it more stable. So that's where nitrification happens. The nitrification is the process of converting ammonia nitrogen into nitrate nitrogen. So nitrate is more stable form of nitrogen. So what you call nitrifying bacteria happens. So we'll study this little later in detail. And denitrification, as you know, is the same thing. It happens in the anoxic thing I already explained. It's converting nitrate into nitrogen gas. So BOD is a substrate. So BOD is the food. As we call it a substrate that's used by the bacteria for their cell multiplication, and in that process they consume and then do the nitrification or denitrification. And the suspended growth process, the attached growth process. So this is the suspended is the one you see in the normal activity slash process. All the let's say the sludge and the particles are suspended. So this type of treatment process called suspended growth. But there are some where we try to attach the bacteria to grow in certain, the objects. So rotating biological contractor also, there's one same you can use a lot of the plates to put it inside. Water passes through this kind of plates. Bacteria grow inside on the surface of those objects, and then when the wastewater comes with the organics, they just eat. So the bacteria colonies are fixed in an object, so that's called attached growth. Okay. So okay, the aim of the wastewater treatment, of course, is to basically remove the solid that's present in water. You'll see that only 99.9% is water, and only 0.1% is solid. So this solid is where we have to spend a lot of time to remove, to just make separate from this water. So solids have organic and inorganic. Okay, so the organics can be in the form of carbon, carbohydrates, fats. Whereas inorganic, when in the form of sediments, it can be in colloidal inorganic suspended solid, salts, and also you can metals or heavy metals. So organic here can be BOD. Now we may have, say, like for example, organic maybe BOD maybe 300 up to maximum, as you seen earlier, and COD maybe even 1000 milligram per liter. So with the treatment, you want to bring, usually the standard is that you have to make the BOD less than 5 milligram per liter from 300. From COD, from 1000, for example, it should be less than 50 milligram per liter. Total nitrogen, depending on the countries of your, let's say, standard, some countries may have less than 10 milligram per liter. Okay. And phosphorus should be less than 1 milligram per liter. Why phosphorus and BOD is important? You know that, right? If BOD, if you release in the environment, let's say they will, the microorganisms will grow suddenly, in the bacteria will grow in the rivers and the streams that where you are putting this wastewater. And then they, in the process, because when they degrade these organics, they will use oxygen. So they will use up all the oxygen in the air, and all the fish will starve of oxygen, and that's why you have a lot of fish killed, right? And what can nitrogen and phosphorus happen? They are nutrients, and they can cause algal bloom, right? So algal bloom is a kind the eutrophication, where it can also suddenly use up all the oxygen, and then what algae can happen is, when algae suddenly grows, like blooms, and then the whole the river system and water bodies is covered with algae, and then they will not let any air to pass through, or the sunlight to pass through, and then the fish and the aquatic environment will be suddenly killed. So that's how you have this. To prevent all this, you have to reduce to this standard. So that's the objective of wastewater. So we have a stages of treatment train. Usually, we similar to the wastewater surface water treatment plant. We have the raw water usually go through preliminary treatment, where you can have the bar screen here and a grid chamber, yeah, and then after you can go to the primary treatment, and you have secondary treatment and tertiary treatment. So these are broad terms used, and of course in secondary, primary, you can have a specific process. Okay, so primary treatment, the preliminary treatment is basically to remove large particles and inert particles and heavy particles, and primary treatment is to let all the settleable solids, especially the settleable organics, removed by sedimentation. And after that, you go to secondary treatment, where object is to remove the dissolved organic matter. Okay, Here you remove the, in the settlement, you remove the heavier organics, and here you remove the dissolved and suspended organics using bacteria, okay? And 95% of is in the form of a suspended solids. So then we have tertiary treatment, where we basically need to remove more of the remaining biological or what's the organics present, or any the microorganism present in the, and then used for disinfection, so that you can have a much better quality of water. So in many countries, the wastewater treatments are usually after secondary treatment, okay, secondary treatment, and after that they disinfect and discharge. But usually tertiary is only limited to many developed countries, where the effluent discharge standards are more highly stringent, and then they have to meet those requirements before the discharge. So that's why they have to have a tertiary treatment. So basically, we will be talking more about the tertiary treatment, okay? So this is a conventional activated sludge process, okay, that you have up to a secondary treatment, okay? Here you have primary treatment, and no, sorry, preliminary treatment. You can have, okay, this one, okay, you may have a pump that's coming from the what's say, the pumping station, okay, pumping station, and then you have all these grills to remove the different types of particles, and then bar skin, of course, to remove those large objects, and then there's grease and grit removal. Then it goes to primary settling tank. So we call it also primary clarifier, where all these heavier solid organics are settled. So fecal matter, especially from the toilet, a lot of fecal matter comes, that much heavier. So they will settle at the bottom, and then they can be taken for a different treatment here. So in that way, you separate from the water. And then once it's the fluid, the liquid coming from there, wastewater coming from the clarifier, will have a lot of dissolved organics. So this is where you require, with the help of the microorganisms, to do so. This is where the activated sludge process is here, okay? Here you have provide a lot of oxygen, because if you create a very oxygen rich environment, then this bacteria will really grow. They really like it, because food is abundant, oxygen is abundant, so they will multiply like, yeah, really fast. And then the higher the multiplication rate is, the faster they will consume the organics present. So you have, once this is what's say, activated in the sludge, activated sludge process, you have the treatment, and then the sludge, you have in the form a lot of bacterial cells and all mixed together, suspended solid. So then they go to the secondary clarifier, so the secondary settling tank, where the sludge is allowed to settle after letting it stay for a few hours there. So all the settled sludge here is very rich in microorganism, because you're drinking directly from here. So that sludge has contains a mix of all this suspended solid, which is not degraded, and also active microorganism. So if you just throw all this, then you are just wasting the active microorganism, which is very hungry to eat your organics, right? So why waste it like that? So initially, people, they just used to throw it, waste it like that in one way, okay? But then later on, engineers realized, no, why we waste this? But if you feed in, what happens? If you return some part of the organics, so they pump some part of the organics back to the bioreactor here, and that's why we call the term is activated sludge process, because your activated sludge is being recycled back, and then you keep maintaining. So in that way, you can constantly maintain the cell number here. So if you want to maintain a certain number of cells, say for example, the cell you want to make, okay, the active microorganism in terms of mass, if you want to say, I want to maintain active microorganism maybe around, say, 5 gram per liter here, then if you keep washing it out, then you cannot maintain it, because it will take time to grow. So in order to maintain the same one, because you're wasting here, then you recycle that. Okay, in that way, by recycling, that recycling rate is controlled to maintain certain amount of sludge here. So which means if you operate at 5 gram per liter or 5,000 milligram per liter, by recycling that sludge, you always constantly maintain that, so that in that way your treatment process is quite active. So whatever does not require, you remove as a waste activated sludge, okay? Then after that, you after the secondary clarifier, then you can have a sand filter, like similar to what we did for wastewater, surface water, sand filter or multimedia filter, whatever, and then you disinfect and then discharge it. Okay, and the sludge that is produced from primary clarifier and secondary clarifier, they do further process treatment to remove the organics, because you can't just throw it in the landfill, because that is contains still a lot of organics. So what they do is they do anaerobic digestion here. Okay, anaerobic digestion here, and then they produce a lot of the energy, biogas. Okay, they use that biogas to even run a generator and then supply energy to the back to the plant. In that way you can offset some of the energy, and but still some part would say part of that one will not be biodegradable, cannot be converted into the methane. So that part will be, again, what they do is they dry it, thicken it, and then sometimes in some countries they burn it. Okay, sludge, because they cannot have produce and landfill it. But in some countries, like in Australia, what you do is after that they landfill it. Okay, after they dry it, and then they landfill it instead of burning it. Okay, so this is the conventional activated sludge process. Or any question you have on this? Okay, so if you're not, then okay, let's go to the next. So these are some of the different treatment options or the process options that you have. Okay, so for example, primary treatment is chemical precipitation, can also be used for neutralization. Use chemicals, grit chambers, gravity sedimentation, the options that you can provide. Secondary treatment is either you can have anaerobic treatment and aerobic treatment, a combination, or you can only have aerobic treatment, or you can only have anaerobic treatment also. But of course, depending on that, which process combination you provide, your water quality will, treated water quality will be different. Okay, so under the aerobic treatment, you have a lot of anaerobic treatment. You have anaerobic digestion, you have packed better anaerobic reactors, or UASP, we call it upflow anaerobic sludge blanket. So those are different types of anaerobic processes out there. In aerobic treatment, also there are plenty of different types. Okay, it's called extended aeration, activated sludge process, or submerged aerated fixed flame process, trickling filter, sequencing batch reactor, oxidation ditch, soil biology, microculture. So these are different types of aerobic process that you can design. Okay, so the choice will depend upon, of course, let's say the economics. How some of them are expensive, some are cheaper, but some are cheaper to construct, expensive to operate. Some are expensive to construct, easier to operate. So different combinations can be possible. So that will depend on the client's needs and also the designer. Okay, and tertiary treatment can be disinfection is one, filtration is one. Okay, then dechlorination is also required sometimes to remove that if there's too much chlorine, that can also impact. Ionized change, electrodialysis, reverse electrodialysis, and also of course you have a membrane process here. You can have MBR process here, nanofiltration, the reverse osmosis if you want to use for recycling. So all these are the option objects that, but yeah, for advanced or tertiary water treatment. Okay. Okay, so yeah, of course you can go through this one. I don't want to really talk in details. So these are the typical wastewater, raw water that's coming in, and the effluent that you're expecting from a wastewater, secondary wastewater treatment plant, conventional activated sludge process. You see here, for example, somewhere in the median raw wastewater here, COD is 550 milligram per liter, BOD is 275, and then you reduce it to, after activated sludge treatment, after 40 milligram per liter, which is less than 50, right? And then BOD around 5. This also reasonably within that. Total suspend is only less than 5, and yeah, so those are all other. You can see that it is within significant removal here. So this should meet the effluent discharge standard of the country that you are designing for. Okay, so what's the main purpose of the activated sludge process? So it's two major things happening in this activity slash process. So we have just removed this part, for example, okay? We have just removed this part. Okay, let's focus on this too. So this is where the activities, so when you talk about activity slash process, you are referring to these two combined processes, okay? Bioreactor and the clarifier, because they work almost together, because whatever the active microorganisms that you maintain here is coming from the return activities, what's the clarifier here, okay? So what's the purpose of this one is to mainly to oxidize and remove BOD, okay, biological organic matter, okay? So that's usually the form of dissolved organic matter, because whatever is settlable is already been removed in the primary. So only what is not removed is dissolved and the suspended one. So that's how the suspended solid and dissolved organics are removed by this activity slash process. Other is the oxidation and removal of nitrogenous matter. Okay, nitrogenous. So that's the nutrients, nitrogen. So what we do here is ammonia is converted into nitrate. Okay, ammonia is converted into nitrate. So what happens here is, as I said earlier, ammonia is using this nitrifying bacteria. So nitrifying bacteria also require a lot of food. So in that way, they will, whatever proteins and whatever the additional carbon is left, that's coming from the if that's in the reactor, that's coming from the wastewater from the primary clarifier, they will use that as a source of food, and in the presence of oxygen, then they will convert nitrogen into ammonia into nitrate. Okay, so in this reactor, two things happen. One is the removal of organic matter and converting the ammonia into nitrate. So what happened is decomposition of organic matter plus the denitrification of nitrification of ammonia. So these two things happen of course, in the process when the cell divides, they also use other nutrients like phosphorus. Also, it's consumed. Okay, so in that way they are removed. Okay, so most of the biological treatment plant in most of the wastewater treatment plant is based on the activity slash process. Okay, so many countries, the full treatment plant is based on activity slash process. Of course, some countries, they may have only up to primary treatment. They don't have a secondary treatment. So it's still like even in Sydney, Malabar treatment plant, they used to have only up to primary treatment. Like they didn't have to have secondary treatment, but now they have a secondary treatment, as you will see in your work later on. So this activity slash process was discovered in England in 1913 by a person called Arden and Lockheed. So these two guys are the responsible for actually inventing this process. Okay, of course, this process is there in nature, but they how really activated it by recycling the sludge and maintaining that cell number in the bioreactor, and then in the way controlling the process to really keep the system active, and then in the process remove the organics from the wastewater. So ASP is a form, aqueous slash process is a form of aerobic biological treatment for removing BOD. So we already discussed this, and BOD as well as nitrogen and phosphorus. So you have to, in order for process to have, you have to provide a lot of aeration. I said it has to be under a very active, rich oxygen environment. So that's why we have to put a lot of air bubbling. You see in the activity slash treatment plant, the water is really churning up, because that churning is because you are bubbling the air. So they have a lot of air diffuser at the bottom. And then, the air, how you provide air is out there, different technology. Some surface aerator, they just rotate and make that air from outside, but some mostly are blowing air from down, diffuser, and then mixing the air. And so, the problem is also that the water has very limited oxygen capacity to dissolve oxygen. So it's very small amount. So that's why you have to constantly keep doing it. because if you over aerate, it will not dissolve. Everything will be wasted also, and then it's the energy will be wasted. So in that way, you have to have a optimum air blowing, so that whatever you blow is used by the dissolved and used by the microorganisms instead of being wasted. Okay. And okay, so activated starch is generally used as a secondary treatment for suspended solid and dissolved organic matter. So we already removed this. So this is also BOD removal of a conventional activated sludge process around 90 to 98%. Okay, and total chiral nitrogen. So that chiral nitrogen is the organic nitrogen plus ammonia nitrogen. So ammonia nitrogen that removal through diatomaceous is also around 90 to 80 to 95%. And total removal is 65 to 90%, and pathogen removal is the order of 1 to 2 magnitude. So which means like really significantly order of magnitude means it's 10 to the power so that's a very high removal rate of pathogens. So this is say the same thing. Okay, fine. Now, so you see this is where the surface area, the aerators are, not surface, the diffuser, air diffuser. So you have a lot of this kind of, because this has a lot of holes here, and the diameter of hole is also controlled to how much air it can blow. So you have at the bottom of the area bioreactor tank, you have this kind of diffusers, so that will blow the air. Okay, and also there's some surface aerator that just mixes air on the surface. That's other way of doing it. But usually this is more efficient because the air is traveling from bottom to the top, and in the process the more air has a contact time with water. So there are many different species of microorganism. It is, as I said earlier, so many different types of species of bacteria will be involved in the removing the BOD here. So as bacteria consume oxygen, they multiply the cell, become more and more, and then they become coagulated and form larger flocks, and that's how they settle at the clarifier, and then it's removed. So I think this is just a repetition of what I already explained. And so as I said earlier, in the activated sludge process, you have a bioreactor here where you put a lot of oxygen-rich environment, and then a lot of cell multiplication happens. The BOD coming in becomes as a food. They grow in that, and then they multiply, they become heavier, and then go to settling tank as a secondary clarifier. They settle at the bottom. Some of them are returned back to the aerator to keep that same cell number, and whatever is not is wasted, and then you get a clear effluent, a secondary effluent that to be either you can disinfect or send it for advanced treatment. So what are some of the biochemistry happening here? Okay, so in the presence of oxygen, the microorganism convert organic matter into the following. Okay, so this is the because it's a complex organism. It has I don't have an exact formula here, but it contains carbon, oxygen, hydrogen, and nitrogen. So that is the main composition of organic matter. So this acts as a BOD. In the presence of oxygen, which you provide through aeration, they convert into the byproduct will be carbon dioxide, then this will become ammonia, right? And then new cells are formed, okay? New cell. So this is the formula for the cells being formed in the cell multiplication of the bacteria. And plus energy is produced because that energy is used by the cell, by the microorganisms for new cell, and then for their respiration, okay? Also, and then in that process, the bacteria consume substrate, which is BOD, and multiply by binary fusion. So how they multiply is 1 becomes 2, 2 becomes 4, 4 becomes 8, like that. So binary fusion. So you can do calculation after how many hours, how much it will be, how much it will multiply up to. So when both BOD food is depleted microorganisms, okay. So as it the process happens, if not enough food is coming from out the BOD, then you already have a lot of microorganism which is already grown, right? Now but they have to live, right? They have to live. So what they do is they eat their own dead cells, like, so microorganisms eat their own cytoplasm to maintain their cell activities. So they call it this endogenous decay. So this is microorganisms, the formula that we give here. And in the presence of oxygen, they consume their own cytoplasm to produce carbon dioxide, water, and carbon, the ammonium bicarbonate. So that actually, this gives ammonium bicarbonate. So in the water, so this will increase the pH, okay, of the water, of the water. So this will increase the pH of the water. And so what can happen is that when pH increases, so this the ammonia will not convert into ammonium, NH4. So NH4 is more stable form of nitrogen than NH3. So NH3, as you see from here, is a gaseous form. In high pH environment, high in pH environment, then this will be loose, volatile, and then lose as a in the air. So that you don't want to happen, because this will be toxic to the environment. Also, it will contribute to greenhouse gas emission, and also we are losing nitrogen from here. So that you shouldn't happen. So in that way, we try to control the pH so that pressure doesn't exceed, so that this water will, this ammonia will convert into. That's why we have to have a nitrification, so that we convert this one and this one into nitrate. Okay. So ammonia results in the odor problem. This is ammonia is toxic, and it's also odor, pungent smell, and toxic to the environment, and it has to be converted into nitrate, which is less toxic, okay, by nitrification process. So a wide range of microorganisms responsible, as I said, and these are some of the bacteria that is responsible for removing the bacteria BOD in the wastewater, and in the process, of course, then also consuming the nutrient, because they also consume the nutrient, nitrogen and phosphorus, because they require for their own cell multiplication as well, right? So in that process, the organics is removed, the nutrients also removed. So mixed liquid suspended solid. So this is one of the important parameter for this activated sludge process. So the amount of sludge that is present in the wastewater in this adiabatic bioreactor is the mixed liquid suspended solid. It's a mixture of liquid and the suspended solid, right? So that's why it's a mixed liquid suspended solid. So the mixture contains BOD that's coming from the primary treatment here. That's fresh coming from there. So it can be dissolved one and suspended solid one, right? And then some of them that is written from the activated sludge process. So that's a combination. So MLS is a combination of BOD coming from here and the sludge written from the secondary clarifier. So it has a lot of active microorganisms. Some are organics, some are inorganics also, suspended particle, and some are active microorganisms, okay? So higher the MLS is so concentration can be between 2,000 to 4,000 milligram per liter in activated sludge process. So this is the usually the optimum condition in which the activated sludge is operated. If you go beyond that, then there are some process implications. So you require more oxygen, and of course your microorganism number will significantly increase here if you increase this from, say, for example, 4 to 5 or 6,000 milligram per liter. Your active microorganism will increase, and then the degradation will also increase. The treatment capacity will increase also, but then also it requires more oxygen. Then you have to provide more oxygen. So that sort of is how the process optimization will work out to see which is the best fit. Okay. And high concentration will, of course, require the lower footprint as well. Okay. So instead of operating at 2,000, we should operate at 4,000 or 3,000, so that you can reduce the footprint. Footprint means the space, right? But you cannot go, as I said, certain high concentration, because it will be limited by the oxygen, because you cannot provide enough oxygen, because the water has the limit to solubility of oxygen. So the maximum concentration is limited by the ability to dissolve oxygen in the water. And also it takes sometimes it takes longer to settle the sludge, because when you have too much sludge, very thick sludge, a lot of sludge, it takes more time to settle. So you require a larger secondary clarifier. So that's also another problem that we have. So this type of problem, this type of problem you'll see when you replace with membranes, you can solve most of the problems this activity, the conventional activity sludge process they have. So sludge volume index is one important parameter that you have to determine usually in the treatment plant, because that gives you an indication of whether your treatment plant is really working fine or not. So sludge volume index is defined as the volume of sludge occupied by 1 gram of activated sludge after settling the aerated liquid in 30 minutes. Okay, if you have, say for example, you take in the mixed liquid suspended solid, you take 1 liter of mixed liquid suspended solid and let it settle for 30 minutes. Okay, let it settle for 30 minutes. You have this much amount of settled sludge. So say for example, you have around from 1 liter of suspended MLSS, you were after 30 minutes, you are able to settle up to 330 ml. Okay, so this is clear water and then this is sludge. So this volume is important for calculating the suspended solid. So which means the SPI is equal to, which is given in ml per gram. Okay, how much volume it occupies by gram of sludge. Okay, so it means that. So we have settled volume of sludge, which is the how much is settled here divided by suspended solid concentration. So how much was the gram? Okay, so for example, if this was 330 ml of sludge that has been settled in 30 minutes from 1 liter, and when you do that, filter that sludge only, and then you measure how much was the sludge there, then if it was just 3 gram of sludge occupying 330 ml, so your sludge volume index will be 330 ml divided by 3 gram. That gives you 110 milliliter per gram. Okay, so 1 gram of sludge will occupy 110 ml of water. So what do you think? For your treatment plant to be good, effective, I mean, if it's working properly, do you think that your sludge volume index should be more or less? But higher is better or lower is better? So can someone tell me? Anyone? Anyone want to try? Okay, everybody's shy. Okay, that's fine. So the lower the better, because if lower means actually if you have volume sludge that the settlement is volume is less, that means it's settling faster. So that better it is, right? So it's easier to remove then. So if this 330 ml is going down, say instead of 330, you have only 50. Okay, you have only 50, and then the 3 gram in 50 ml. That's very effective way of settling. Okay, so the smaller the value of SPI, the better it is. So some of the operating parameters is okay. So one is dissolved oxygen concentration. So we must have a sufficient dissolved oxygen in the water and then we provide that through the aeration. Okay, so that you have enough BOD removal, organic removal. Usually it's set at around 2 milligram per liter in MO, in milligram per of oxygen in water, because that's the solubility limit of the water. So if you can't increase more than that unless you change the temperature of the water. Okay, so that's how this limited. As I said earlier, the activated sludge process, you cannot really have very high concentration of MLSS because you take a lot of oxygen, but the water cannot dissolve more than 2 milligram per liter. So that's the limit that water can, So if this is limited, then you cannot have a high DO, because that will waste the energy, because whatever you provide in the form of aeration, the water is not going to retain that oxygen, so it is just blowing out. So it's a waste of energy. And also, if you provide too much oxygen, more than what the bacteria required, then a different species of bacteria will be growing in the bioreactor. They call this kind of filamentous bacteria. So they are very network kind of bacteria, not the individual one. So this network kind of thing is very fluffy and then very light. And then when they grow in size and then become network, they increase the buoyant force and they don't settle it easily in the settling tank. So you have a problem in the settling tank, not being able to settle this filamentous bacteria. So you don't want to have that to be happening in the treatment plant. So that's why you don't want to aerate more than what is necessary. And also you don't want to have too low dissolved oxygen, because if you do that, then there is not enough oxygen for the BOD removal. And also it can create an anaerobic condition, because anaerobic condition means when there is poor oxygen, then instead of aerobic bacteria that grows, the anaerobic bacteria will go, and then they will produce hydrogen sulfide and also some methane. So that will be smelly. It creates a very smelly environment. So I've been talking very long, so maybe if somebody wants to ask a question, yeah? Yeah, we can, it has to be interactive. Nobody asking me any questions. So either you understand everything or that you understand nothing, yeah? Okay. Time is 12 o'clock. So maybe we can go up to 12:30 and then, okay. So operating parameters. So hydraulic retention time is another one. Okay, this is one of the important parameters. So how long the water stay in the reactor, that is the hydraulic retention time. Usually it's about 4 to 24 hours, depending on the process design. If you make it too short, then you have not enough time for the bacteria to remove the organics. So that means you will have poor quality of effluent, that wastewater coming from there. And yeah, you don't want to keep it very long time, because then it requires very large tank. Okay, so it has to be, the optimum should be, working within in between. So HRT will be is equal to volume of the reactor volume, the reactor volume. So for example, if this is the reactor volume VR, then the flow rate that's coming in, so that will give you how much time it has. For example, VR will be in meter cube. Q, flow rate coming in, will be meter cube per hour. So meter cube meter will get cancelled, and H hour goes up, so that becomes a time. So this will be give you how long in terms of time the electrician time is. Okay, so if you have if a flow rate coming in, going out here, and then is the water retaining here, so that will, hydraulic retention time will depend on the size of the reactor and the flow rate that's coming in. Okay, solid retention time is another one. Okay, solid retention time, or sometimes we call it mean sales residence time. So is the calculation how long the sludge is staying in the reactor. Okay, earlier we had how long the hydraulic fluid is retaining in the water. So that is hydraulic retention time. But this is the solid. How long the sludge is staying in the sludge. Because you remember we're recycling some part of the sludge in this process here. It's not all that. If it is one way, then okay, hydraulic retention time and sludge retention is maybe quite similar if everything is going there. But some of them we are returning it. So in that way, the sludge retention time is much higher than the hydraulic retention time. Okay. So usually it's about 2 to 8 days for effective BOD removal and the nitrogen removal. If you want a neutron removal, you require a much longer hydraulic, sludge retention time. So if you target only BOD removal, so it can be a little less. Okay. So sludge retention time will be given by this equation. So VR is the volume of the reactor into the MLSS concentration divided by how much sludge. So this gives you the amount of sludge, mass of sludge, this is in the reactor, divided by how much is being wasted out. Okay, how much is wasted out, taken out, and how much is removed as effluent. Okay, because after the treatment, some will go, like to the filter. So how much is wasted from as effluent and how much is wasted as the sludge waste. So some, because most of them are returned back. So that gives you how long the sludge is staying in the reactor. Another important parameter, operating parameter, is the food to microorganism ratio. Okay, food is the BOD is the food, right? How organic is coming, and M is the microorganism ratio. So that ratio is very important. You know, if food is less, if your microorganism is too much, then your microorganisms will starve, right? So then they will eat their own cytoplasm. They will eat, so many will die off, right? After some time. So you want to have maintain that ratio all the time. So it's the kg of BOD per day biomass in the reactor, and then okay, so it should be like the food to microorganism ratio should be between 0.2 and 0.5. So that means for every what say 0.2 to, so which means your microorganism to food ratio should be, if you say your food is 2 gram or something like that, then it should be air, say how much it should be, so 10, right? 10 times. So that ratio has to be maintained. If you have too high food to microorganism ratio, as I said, you cannot, microorganism can't, so food is too much, right? If the food is too much, microorganism cannot handle all the food. So which means you'll get more food coming, that more organisms coming in the effluent. So if it is, yeah, and if you have also it will result in bulking of the sludge, and because the organics may be less, the food that is not eaten, it may become that kind of problem in the sludge, and then they will not be easy to settle. So you have a poor settling of sludge if you have too much food and insufficient, what's say the microorganism. If it is too low, okay, it's too low, which means you have too much microorganism and too less food, then it will also result in the growth of filamentous bacteria, as I said earlier. When you have too much oxygen, yeah, then you have filamentous bacteria growing. If you have too much, too low food and too much microorganisms, then this filamentous bacteria seems to survive more than the other bacteria, and in that way you have very poor settling of the sludge. Okay, so the food to microorganisms ratio can be calculated by this one. So Q is the flow rate, La is the organic matter that's coming in, right? BOD coming in. So BOD, that means the mass of the BOD coming into this one divided by the mass of the reactor, or the mass of the MLSs in the reactor. So that gives you food to microorganisms ratio. Okay, so remember that it should be between 0.2 and 0.5. So nitrogen removal, okay, neutron removal. So neutron is in the form of phosphorus and nitrogen, okay? So mainly nitrogen, because nitrogen is very high concentration when you compare to phosphorus. So nitrogen comes from organic nitrogen, okay? So if you have a protein that's coming in the water, wastewater, so protein has also nitrogen. As you decompose protein in the reactor, then the nitrogen will be released. Okay, so also nitrogen comes from urea. Urea that is present in the urine. Okay, and also various dead organic matter. So when the cells they die, yeah, then they also release nitrogen they have. Okay, so nitrogen is mostly in the form of ammonia nitrogen or ammonium or ammonia. So that is depending on the pH. If you look at this pH curve here, if your pH is higher, okay, at higher pH you will more in the form of nitrogen, ammonia, gaseous ammonia than ammonium. So if you want to be in ammonium, which is more stable form of ammonia, nitrogen, then it has pH is to be less than 7. So if your pH is around, say, for example, around 11.5 or 12, then everything is ammonia, and then all your ammonia will be volatile and then released to the environment. Which is not good. Okay. So that's why ammonia has to be that's the other nitrogen form will be nitrite and nitrate. So ammonia will be converted into nitrite first and then into nitrate. So there's a process during the nitrification process we'll see a little later. Okay. And so that's dissolved in water. Also, sometimes nitrate and nitrate is also already there in the wastewater. So the other form of nitrogen will be total inorganic nitrogen. So ammonium nitrogen may be already there. Also, this may be already there. So these are ammonia, ammonium, nitrite, and nitrate. They are all form of inorganic nitrogen. So total chiral nitrogen, I said, is organic nitrogen that's coming from proteins, plus this nitrogen, this gives ammonia nitrogen gives you total chiral nitrogen. So total nitrogen is the form of all forms of nitrogen, okay? So that is the nitrogen that's present that which it has to be removed in the organics, okay, in the activated sludge process. The phosphorus is present in the form of organic phosphate, that is a bond organic matter, okay? And then also usually in the form of polyphosphate or orthophosphate, usually in the form of orthophosphate because it's in the form of ions. So you'll see that PO3, this maybe let's say it is usually maybe in the form of, say, for example, ammonium phosphate or say calcium phosphate. If it's calcium phosphate, they will precipitate because calcium, that's how we try to recover phosphate from the wastewater, by trying to combine with magnesium and calcium. So when calcium combine with phosphorus, phosphate here, it converts into calcium phosphate, which is precipitate. And when it combines with magnesium, it converts into magnesium phosphate, or sometimes also ammonia combines together with magnesium and phosphate to give magnesium ammonium phosphate. That is called struvite. So that's also a white precipitate that sometimes you can find when the urine is stored for a very long time. You see that there's a white deposit. So that's all because of the magnesium ammonium phosphate, struvite. So then we have here, this is the form of nitrogen that we have, total nitrogen in various forms, and we have also phosphorus. Then why we need to remove nutrient nutrient removal in the activated sludge process? Because they are toxic to the fish, as I said earlier. So they can form algal bloom, eutrophication, and then it causes a lot of fish dead. I think it happened a few years ago in Australia here. A lot of fish were dead in the rivers. So that was one, algal bloom was one of the problem, because this nitrogen and phosphorus washing out from the agriculture farms, and then there's too much nitrogen, and with certain temperature the algal bloom can happen, and a lot of fish dead. So ammonia also exerts nitrogenous BOD in the receiving water, because ammonia, when ammonia is present in the water, then that denitrifying bacteria will try to act and then use. So they will try to suck up oxygen from the air, okay, from the water, and then they also can kill the fish. And nitrogen and phosphorus act as a fertilizer, so that's how this algae bloom can happen, because they provide perfect nutrients for algae to grow, and certainly very rapidly. So what are the nitrogen removal process here? So we have chemical methods and biological methods. So of course the chemical methods, so we're not talking about activated sludge process, but in there are methods that you remove by chemical means. Here is aeration by air stripping, there's one. We have through chlorination, also one way of removing nitrogen from the wastewater. Ion exchange is also one way where we exchange say the nitrate or ammonium ions and then remove from the wastewater. So these are some of the chemical methods we can adapt. But usually we are talking about in the activated sludge process, the biological method that removes oxygen. So when BOD removal, so when the BOD is consumed by the wastewater, in that process, what can happen is ammonia or ammonium present in the wastewater can be converted by nitrification using nitrifying bacteria and convert into nitrite, and first nitrite and then nitrate. Okay, so then once you just form, nitrate is formed here, and then you send back this nitrate rich water back to the anoxic tank, and there when you don't have oxygen enough, then the denitrifying bacteria will use this oxygen from the nitrate and convert it into nitrogen gas. So that's how denitrification happens. So these are the removal process in the activated sludge process. Okay, so how this some of the process here. You have nitrification. So organic nitrogen is say organic nitrogen and urea, protein, etc. They are the main source of nitrogen in the wastewater. and through hydrolysis and ammonification, they are converted into ammonia or ammonium. Okay, so that's in the form of ammonium nitrogen here, NH4 or NH3N. Okay, so this ammonium nitrogen using the ammonia oxidizing bacteria, we call it ammonia oxidizing bacteria or AOB, such as this nitrosomonas is one of them. In the presence of oxygen, they convert ammonia into nitrite. Okay, first is the nitrite, NO2. Okay, so, and once this is formed, another set of bacteria we call the nitrobacter. Okay, nitrobacter, we also call it nitrate oxidizing bacteria. So nitrate oxidizing bacteria, AOB converts, such as nitrobacter converts in the presence of oxygen, nitrite into nitrate, okay, NO3. So in this, how we have two steps, or three steps actually here: hydrolysis, ammonium oxidizing bacteria converts into nitrite, and then convert from NOB to nitrate. Okay, so 4 processes actually involved here, finally to get a nitrate. Okay, so these are some of the chemical equations that you can use here. Okay, so this is the the protein or the substrate that you have. Okay, source of organic nitrogen here. So you, in the presence of oxygen, you can convert ammonia. So that's called ammonification, right? Like converting into ammonia and hydrolysis. Then you have the cells, this one here, in the presence of oxygen, then they convert into bicarbonate. And then again, this one, in the presence of oxygen, they convert into nitrate. Okay, but of course, this is the short form of bacteria, but this in process in between I haven't shown here. But yeah, so it is a different stage where you get nitrate here first, and then you get the nitrate in the final one. Okay, so final you will get is water, some hydrogen is also released here, carbon dioxide, and then nitrate. Okay, so in the process, what you do is to remove 1 gram of ammonia nitrogen here, so 1 gram of ammonia nitrogen, you require 4.6 gram of oxygen. So to remove 1 gram of ammonia, you require 1 gram of oxygen. Okay, and 4.6 gram of oxygen, and it can form 0.15 gram of new cells from in that process, and it consumes 7.14 gram of alkalinity. Okay, and also it consumes around 0.08 gram of carbon is consumed, because they have to multiply the cell and they use that carbon as a source of cell synthesis. Okay, so we said the many factors affect this, the efficiency of the nitrification, the food to microorganism ratio, as we discussed earlier. Even pH is quite important, the amount of dissolved oxygen is important, temperature is important, and MLS concentration is important. So it's these nitrifiers, especially the nitrifiers, that convert into from ammonia to nitrate, are quite also very sensitive. So they can, so they work in a very limited environment. Okay, so the nitrifiers are very sensitive, so 6.8 and 7.5. So usually in the treatment plant, you have pH control, pH set point. If it's pH is going beyond that range, then it will be automatically adjusted using chemicals present there. Otherwise, your activity/process bioreactor will not work properly. Okay, so some of the organisms are given here, nitrifying bacteria, and then so you can see the types of oxidizing bacteria, ammonia oxidizing bacteria, and nitrate oxidizing bacteria. So now we have how the denitrification process happens. So nitrate we have already formed. So the nitrate, when there is no oxygen, okay, so there's no oxygen, but the cell has to maintain, right? The organism has to maintain. So that meant this food is already there. So the special type of bacteria, they will reduce the oxygen from the nitrate here. So they will strip the oxygen from here. They can first convert into NO2, nitrogen, and then it will become NO or N2O, and then finally this will be released as a nitrogen gas N2O. So in this process, when happening this one, also require a lot of BOD. If there is not enough BOD, this process will not happen. So that's why what happens is that usually nitrate, because the wastewater in the pure form, the fresh wastewater doesn't have nitrate much. Okay, so through biological nitrification in the bioreactor, a nitrification happens and nitrate is formed. Right now, that nitrate has to be reduced. I mean, to remove that nitrate. But after the treatment, there is not much food left because food is already consumed in the bioreactor. Okay, so what happens is you have to send it back to the either you put more food after that, so which means if you want to have denitrification after the reactor, okay, after the sedimentation tank, primary, secondary qualifier, then you require food, so you have to add food, but that's expensive, right? So usually they return back it to the primary clarifier where there's more food, okay, and then the denitrification happens over there. Okay. Okay. So you see here, that's what happens here. So denitrification is usually after before the aeration tank here. Okay, that's how I was saying here, because the nitrification happens here. And so if you want to have denitrification happening after this, then there is no more food left here. So that's why some part of the effluent here is sent back to what we call an anoxic tank with the denitrification. So where we don't provide oxygen here, but the nitrate is there, and then that nitrate will be through when the effluent BOD comes here. So some part of the nitrate will be stripped off, and then nitrogen gas is released. So all this bubbling can happen, and in that way you reduce the nitrogen from the effluent system. So remember, when you treat the nitrogen, when you have nitrification process happening in the activated sludge process, nitrogen is not removed. Nitrogen is just converted from ammonia nitrogen to nitrate nitrogen. The only little is removed because it is synthesized with the cells. Some of them will become cells in the part of the microorganism. Some will be wasted as a sludge waste. So it will go together with the waste, okay, sludge waste. But still significant amount of nitrogen is there in the effluent here. Yeah, so it cannot be removed unless you send it back here and then send it to the atmosphere. So that's why you have an anoxic tank here to remove the nitrogen from the system. Okay. Okay, so advanced water treatment is required. So why we require advanced water treatment? Okay, wastewater treatment is required. So we require this one in order to meet the stringent regulations. Okay, so they have a conventional treatment plan, and sometimes with progression, the country can keep improving their standard, and then they based on more research and more evidence, they instead of nitrogen 10 milligram per liter, we have to have less than 5 milligram per liter. So in that, when that happens, your conventional treatment plant cannot achieve that. So you have to have additional advanced treatment to remove those. So this is the reason, one of the reasons when we require advanced treatment. And advanced treatment may also be required because you want to reuse the water, recycle the wastewater, and reuse for some non-potable purpose, for irrigation or irrigation of the parks, maybe for water recreation, or so many other things that you don't have to really drink it. Maybe toilet flushing, okay? Because toilet flushing, you don't require clean water. So in that kind of situation, why not recycle the water if you really treat it? Because secondary treatment does not remove as much of the organic pollution in water, so advanced treatment is required. Okay, sometimes your secondary treatment plant may not work properly as designed. So in that case, you may have to have additional process like this advanced treatment. So advanced treatment is for removing organic or suspended particles, and also remove nitrogenous organic demand from the water, so nutrients and all. Nutrient removal, nitrogen, phosphorus, and also to remove some of the toxic materials. So if you have the wastewater treatment plant here. Okay, so you have this is, say for example, you have a screening. There's the preliminary treatment with primary treatment here. Then you have secondary treatment activity / process, and then the advanced treatment can be either the extension of this. So you use the same one here. Okay, you further treat using membrane, okay, membrane filtration, and then you can further, after that, either you can discharge it to the environment, or you further treat it, reverse osmosis, and make this use of water for some application. So here you can, if you treat like this, then you can have a better quality of water that you can discharge to the environment. So you meet the effluent discharge standard, or if you want to apply it for water recycling and reuse, then you can have the further treatment, disinfection, and then apply it for or beneficial wastewater reuse. So this is the form of advanced treatment in addition to the treatment existing treatment plant. Okay, so it's now time is 12:30. So how about we break for lunch? I'm sure you're hungry. So let's break for lunch for 30 minutes. We resume the lecture at 1 o'clock, and we'll do a membrane bioreactor, and then do some the research work that we have done briefly, and then we'll do an assignment and finish off at 2. Is that okay? Okay.
Yes. Yeah.
Okay, so have a good lunch, and then we'll see at 1 o'clock then.
Yeah. Thank you, Professor.
Okay. Let's see. So we're putting here, and I'll. Okay, welcome back. So have you had a good lunch? Okay, so let's continue with the membrane bioreactor. So you can hear me and see my slide, right? Because I don't know whether you can see or not. Are you able to see the slide?
Yes, we can, yeah.
Okay. So membrane bioreactor. So membrane bioreactors is actually a combination of membrane and the activated sludge process. So it's a unified system of the conventional treatment process with the membrane. Okay, so usually so when in the conventional activity sludge process, what you have is usually you have bioreactor, which is anoxic plus aeration here, and then followed by clarifier, and then you have filtration, right? So what happens is the filtration definitely can replace by membrane, and even it replaces the clarifier. So you don't require a clarifier after the bioreactor. So membrane replaces actually these two, yeah, these two processes. So it's quite a saving of the space. And the main, so if you remember our earlier the objective of activity sludge process is to produce a settleable sludge, right? The sludge that gets heavy and then be able to settle easily in the settle and the secondary clarifier in this. So if your sludge is not settleable, then you will have a problem not able to settle, and then most of those sludge wash out, right? So what happens with this one is that if you replace with the MBR, then you don't have to have a settleable sludge. That's not the objective. So you can have any sludge is fine, suspended, so because membrane is just filtering it. So in that way, the idea is not to have a settleable sludge, but any form of the sludge is fine. You know, just filterable sludge is fine. And so when you replace this kind of let's say membrane bioreactor MBR, you have, of course, you still have to have that fine bubble for aeration of the bioreactor, but on the top of that you also require some kind of aeration for the membrane, because membrane, otherwise the all this sludge will MLSs will stick on the membrane surface, and then reduce the membrane, create the membrane fouling, and they reduce the water flux. So in order to have, you have what we call it coarse and larger bubble, so that will, when you put the bubble at the bottom of the membrane, as the bubble travels up, so that will give a scouring effect and then remove any particle that is deposited. So that's how they try to reduce the membrane fouling. So as I said, by replacing the membrane bioreactor with conventional activated sludge process, you can significantly reduce the membrane footprint. Okay, so MBR is equivalent to aerated bioreactor plus secondary clarifier plus filtration unit. Okay. So these are some of the configuration that you can use. So say, for example, you have activated sludge conventional process, right? So one option is, okay, if you want to advance treatment, you put a membrane filtration after the settling tank. Okay, you replace use the sand filter with some kind of membrane filter. So that's one option, yeah. But other option is that, yeah, just remove both the sand filter and the settling tank, and then replace with the membrane. So just outside, okay. So we call it a side stream. So side stream means the sludge MLSS goes there, filter it, whatever is not filtered, then you go back and then keep recycling here, so you get a clear effluent here. Okay, so this is a kind of or we call it the side stream MBR. And the other option is to provide a submerged MBR. Okay, submerged MBR means instead of putting in the side stream, you put directly inside the bioreactor tank. So in that way, you are still further saving the space. Okay, so instead of having a separate membrane space, you put in the reactor itself. Okay, so that's one we call it submerged integrated. So submerged integrated within the same reactor. But you can submerge can be also outside submerged. Okay, you can have a submerged outside. Okay, you can submerge outside, so you have a separate like side stream, and then again even submerge it. So it's submerged and separated. So these are some of the different process configuration for MBR. So what are the benefits of MBR treatment. So remember earlier, we have to have a settleable sludge for conventional activity sludge process. So that's why you have to be very careful in how much sludge MLSs you operate. If it is too high, then you cannot provide enough oxygen, and then you can have a lot of other problem as well. But here in this case, you can even operate at a very high sludge concentration. If I remember, 2 to 4 thousand milligram per liter. Here for MBR, you can go up to 30 milligram per liter, from 10 to 30 milligram per liter. So typically it's between around 10 to 15 milligram per liter. So in CAS, it's up to, you can go even some of the highest, but usually it's around 4 milligram to 5 milligram per liter in conventional activated sludge process. And also in conventional activated sludge process, SBI is important, how much sludge can settle. But for MBR, that's not important. As long as the sludge is filterable, that is fine. Okay. And also in MBR, you don't have a problem of sludge being washed out, because in the conventional activated sludge process, you have sludge going out with the effluent, right? It's possible. But here, it's the only the output from the MBR is the MBR effluent. So sludge washout is also not a problem. And it can operate at a very high SRT, solid retention time. So if you're, let's say this, you can operate at very high MLS concentration, which means you can also increase the sludge retention time. And you can have a better colloid and the micromolecule removal using this MBR compared to the conventional activated sludge process. And generally, you have a better removal or biodegradation of organics compared to the conventional activated sludge process. And that's why you'll see the effluent quality is much better in the next slides. And also, MBR process is sometimes quite useful, or is capable of degrading organics that are very often difficult to degrade in the conventional activated sludge process, including such as industrial effluent. So industrial wastewater is also treated using MBR. And fluid to microorganisms ratio. So that's very important for a conventional activated sludge process, right? But for MBR, it can operate also very low the FM ratio, which means if you usually if you have a very lean wastewater coming, the dilute wastewater coming, so it is able to treat that. In conventional activated sludge process, that's difficult because you need to have a constant food to microorganism ratio. If your food decreases, then you have to provide additional food, otherwise you will lose your microorganisms. So that's also one of the problems. So this so it is the MBR can produce a very stable, steady, reliable, and a quality with very high effluent. The very high effluent quality compared to conventional activated sludge process. Okay. So you look at here, if you compare this one, this is the mixed liquid suspended solid, and this is the MBR permeate, that is after treating with MBR. So you can see that the water is very clean. The turbidity is less than 0.2 NTU. Imagine the earlier we were talking about should be less than, I think, how much was that? We should, for the, the conventional activated sludge process, it is usually more than 1. But here you can go up to less than 1.2. It's a very clean the effluent. So BOD is less than 3 milligram per liter. Total suspended solid 1 milligram per liter. Turbidity 0.2, and they would have removed most of the bacteria and even the viruses. So usually, in terms of the steady performance of the plant, MBR is much more stable. If you can look at here, if you compare with the activated sludge process, conventional one. Conventional activated process sometimes can fluctuate because even if you have a very good control, sometimes the wastewater effluent can change. Certainly pH can change. So environment change, it will be reflected in that. But usually MBR, you can get a very reliable effluent. And then footprint is very low. Yes, because you are substituting MBR with replacing the secondary clarifier, and the filter. Yeah. So if you remove the filter, which is occupy a lot of space, and the secondary clarifier, the primary, secondary settling tank, which also occupies a lot of space, if membrane can replace that, of course you can save a lot of footprint, and also energy. Of course, that depends on how you operate. Sometimes MBR can also give you a little bit lower energy. Okay. So we don't require primary, let's say. Sometimes you can even process with such a way that you don't have to have the primary settling tank as well. So you can have wastewater directly going to the MBR. So which means you have MBR able to replace. Okay, if I go back to our earlier, yeah. So you can have this one MBR completely remove this. So because here we don't have here MBR. So we remove primary settling tank, we remove secondary settling tank, and we also remove the filter that we used to have, like on a sand filter or some other filters that you used to have in the conventional activated sludge process. So in that way, one membrane replaces actually three different processes. There's a lot of saving in the space. So if you look at the here, this is the original plant conventional activated sludge process. Okay, but if you replace with the MBR, within this area you can have a complete treatment plant without compromising the quality, and even better quality than the conventional activated sludge process. So that's the significant advantage that you can get from putting the membrane processes. Okay, MBR. But energy is actually not really low. It's energy, it can be a little bit more in the process, because when you operate at a high MLS concentration, then you have to provide more aeration energy. And so in that way, you increase the aeration energy, and also you could require vacuum to filter the water, suck the water, and then so that operation cost will go high. So energy consumption will go high a little bit, but you can significantly save from the cost. So especially if the land cost in the area is very high, yeah, this membrane is the ultimate choice. So you can see compare the water quality parameters between conventional activated sludge process and BR. So HRT is less here, okay, 3 to 8 hours compared to conventional activated sludge, which go up to 24 hours. SRT is much higher. Okay, MBR you can retain solids for much longer time. Put to microorganism ratio can be much lower, and MLS concentration can be much higher, so you can have more solid retention times solid in there. So BOD, look at it, BOD water quality is less than 5 milligram, less than 2 here, so it's much higher, better quality. Even suspended solid here and turbidity, quite significant. So a lot of advantages in terms of even nutrient removal here. So that's but when it comes to nitrogen, it may be a little bit different here. So nitrogen, it may be a little bit more in case of MBR. So you will have to have some other arrangement to reduce that nitrogen. But when you're talking about the, let's say, usually after MBR, usually people don't just simply throw the water to the environment. They make use of water for some purpose. So if you use this one for irrigation, that is very good, because you have enough nitrogen for use as irrigation water for plants. And even the coliform here is significantly reduced. But they have some other issues. One of definitely, as I said, membrane fouling. If you look at, if you take out the membrane, you immerse in, the membrane in the reactor, and you just take it out. This is what you will see. Is really a lot of deposits on that, because this is MLSs. In the reactor, you have very thick sludge. So imagine all this will be depositing on the membrane, and it can create a lot of problem with the fouling. So that's why you have to have a air scouring to remove that and reduce. Of course, it cannot really prevent membrane fouling, but you have to just at least control slightly. So that's why energy usage is higher than the conventional activated sludge process. And frequent chemical cleaning is required, using, say, caustic soda and sometimes chlorine resistant chemical cleaning agents. because otherwise if you use chlorine then it can be a problem. It can damage the membrane. So another advantage is that relatively new technologies, MBRS is of course, in many the plants are applied around the world, but still many plants haven't. So it is still a relatively new technology, and just the design standards are still not really standardized, and so there's still people working on it. And some you get very thick sludge and very high concentration of sludge, but sometimes it's very difficult to dewater also. So that's also one of the other problem. But when the in the last how many years, 20 years, the energy required for MBR has significantly reduced. So somewhere in the 2000, it was around 2.5 kilowatt hour of energy per meter cube of water treated through the MBR. But now it is reduced to almost less than 1 kilowatt hour per meter cube of treated wastewater. Okay, so energy has actually significantly reduced. Okay. Now, so some modules here, MBR module comes in this way. So this is just one module. So when you stack several modules, becomes a frame. Okay, so this frame is shown over here, like a combination of a small modules here. So this module is given here, bundle. And then when you stack all these frames, and then you become a cassette. Okay, so this is a member cassette containing a lot of member modules. Okay, so this is called, so you can see sometimes it can be 10, 20 stacks of membrane frames. So this is how then you make it more compact, and then this whole thing can be immersed in the bioreactor. Okay, so these are most of the current membranes are hollow fiber membranes. Okay, hollow fiber membranes. But yeah, there are plants which uses the flat sheet membranes as well. So some of the key design parameters for MBR. So it's the bioreactor size is 1, aeration requirement is 1, energy requirement is 1, or the power requirement is 1, membrane module requirements, membrane powering and membrane performance control, membrane cleaning in life and membrane life and operability, and the chemical dosing requirements. So these are some of the key aspects of MBR design. So let's talk about the design, because MBR is a combination of membrane and the bioreactor. So it's like activity / process, except that the difference here is in the conventional activity / process, that your MLSS effluent goes there, go to the settling tank, and some of them return back, right? But here everything is staying in the chamber, so it's actually recycled within that. So which in this case, of course, this is a constantly activated / process, not recycled sludge. So the design MBR design involved design of the aerobic reactor, anostic reactor, and the MBR, the membrane requirement. So total volume of the biological reactor will be total volume of the aeration zone. That's the where BOD and ammonia oxidation take place, and plus the volume of anostic tank. As I said, anostic tank is usually still slightly before the bioreactor. So in that way, they are usually designed together, but in a separation in between. So the bioreactor will be total anaerobic, the aeration zone plus anostic zone where the denitrification happens. Okay. BOD concentration is one of the measure for the design parameter. Okay, so because they use as a substrate, so it will be in terms of milligram per liter, gram per liter, or kg per meter cube. So you can usually calculation we do in terms of kg per meter cube. BOD load is, now we have BOD concentration and a BOD load. So BOD load is the amount of BOD organics, that mass that's coming in a day. So that's, we call it food in a day. Okay? So kg of food, or there's a substrate in a day. So when you multiply BOD's concentration, which in terms of kg per meter cube, multiply with the wastewater inflow, that gives you the BOD loading. Okay, MLS concentration is the sludge concentration in the bioreactor. SRT, as we discussed earlier, is the sludge retention time, and sludge yield is another parameter that you use for design, is the amount of sludge generated per BOD, okay, of at the end of SRT. So when you release the sludge after recycling agents, after some time, of course, in the MBR, you can't keep the sludge continuously there. At a certain point, we have to remove the sludge, right? Because more sludge will be formed. So you want to maintain at that, say, for example, you want to maintain exactly around 20 gram per liter. So from time to time, you have to waste the sludge. Otherwise, it will exceed the design, and then you have other problem. So and also the sludge will become more stale. Non-active, because microorganisms will die. Some of the food will not be biodegradable. So all this thing will remain in that, like almost like a dead sludge. So that has to be removed. Okay. So how much of that is converted into, I would say the sludge yield is the amount of sludge. So that's of course, the amount of MLS is converted per kg of BOD. How much in the bioreactor? So if you put 1 kilo of BOD to the bioreactor loading, then that will eaten by the plant. The bacteria will grow again, increase the mass, and so that it will increase the mass in the concentration, right, in the bioreactor, right? So how much it increases, so that gives you sludge yield. How much sludge is produced per kilogram of BOD that you load in the bioreactor. The other so we can calculate the volume of the bioreactor. So volume of reactor will be volume of the anoxic tank plus volume of the aerobic tank. So volume of the reactor can be combined together, and they can be calculated using this equation. So that will depend on the BOD loading. That is in terms of kg per meter cube, for example, BOD loading in kg per day. Okay, how much BOD is coming in a day, multiplied by sludge yield. That is how much sludge is converted, how much BOD is converted into sludge, okay, per kg of BOD that you put in. Sludge retention time in the days, and divided by the concentration of MLS in the bioreactor. So if you use this equation, you get the total volume of the reactor, okay? So now you want to find how much reactor is required for the anaerobic zone and the aerobic zone. So usually the aerobic zone, the SRT will be given, how much SRT has to be there for aerobic zone. So if you have given that, then you can find the total volume multiplied by the aerobic zone SRT divided by the total SRT that will be required. So that gives you the volume of the aerobic reactor zone. Okay. So daily BOD load is how do you calculate the BOD loading rate? So BOD loading rate, of course, you have this BOD concentration. So from milligram per liter to, you can convert into kg per meter cube. Okay, and that multiplied by the average dry weather flow. So it's that average flow that in a day. Okay, because there is a peak flow and average flow. So why peak flow? Even though you may use, for example, we have the per capita water consumption in a day, maybe say 150 liters per day. One person is using 150 liters per day, but that's the average, right? So that's average, because you're not continuously using water like constantly. So you're using only from time to time. So most often it can happen in the morning when everybody's able to go to office, everybody's taking shower. So that time the flow will be high. So that time there's some peak area when, so that peak factor will determine actually what is the size of the treatment plant, not the average weather flow, because sometimes during the peak flow you get a lot of water and water flow. So your wastewater treatment plant should be able to handle that peak flow. So this is designed on that. But when you calculate the BOD loading rate, you can do it in terms of the average dry weather flow. So average weather flow, that will give you the BOD loading in terms of kg per day. Okay. So now we want to, now the other thing we got is how much area is required. Okay. So okay, now as we are now designing both for MBR and the active conventional activity slash process. Okay, so this one applies for both whether you're doing MBR or the conventional activity slash process. Now, when you do conventional activity slash process, we have the settling tank, right? We call it secondary clarifier. So what's the area required? So that design, you can use this equation, how much solid load is coming there. So that solid load is that is coming from MLSS, right? So because MLSS, what is directly going to the secondary clarifier. So what is the loading there? So how much kg of that solid is coming per MLS is coming per hour? So divided by the maximum loading rate. How much you're allowed to load. So that will be given usually the design standard, okay? And into number of clarifiers, how many clarifiers you want to have. So that will give you the total area required for the suspended, for the secondary clarifier, okay? The solid loads you can calculate like this. Solid load will be the maximum flow rate, that's the peak flow rate multiplied by the MLSS concentration, okay? That's because that's coming to the, so we have to use this MLSS high concentration because at that instant, that much flow rate will come to the secondary clarifier, let's say the clarifier, and that has to handle that, okay? So how do you calculate maximum flow? So maximum flow is the peak. Usually there's a peak weather flow, right? Peak wet weather flow. So that's what I'm saying. Peak weather flow will be, sometimes it is, many people are using the water at the same time. So that will be the peak flow. Sometimes, even during the rainy season, what some of the rainwater stormwater can come into the sewer lines and then increase the flow rate. So usually it's around 2 to 3, factor of 3. So if your average weather flow is around, say, 1 meter cube or 1000 meter cube per day, then your design for the peak factor will be around 3 times or 2 times that, okay? So maximum flow rate will be peak weather flow rate plus the return activity sludge, okay? So here, if when you are designing this one, okay, right, for example, when you're designing this one, so some of the sludge will be written back, right? So that's why you have to consider that also. So that will be the peak flow coming to this one. So the flow that you're getting in that's coming to the secondary treatment plant will be whatever is coming from up, that will be peak flow, plus also that you have recycled here. So that will also have to be added because that comes to ultimately come to the secondary treatment plant. So that's how you'll get Q maximum is equal to sometimes, if the peak factor is 3, then you get around 4 times the average dry weather flow for the maximum. So even usually the average day weather flow, for the return activity sludge is around 1 times average dry weather flow. Okay, but of course you can adjust it, but you can take it as around just for the calculation. So now the other thing is, so if you are a membrane, how much area you require for the membrane. So that membrane design will be how much total membrane area required will be, what will be the peak wet weather flow that happens during the very peak time, how much water will flow, and then divided by the membrane area, okay, the peak flux. So what the peak flux that you can operate. So you have an average flux that you have to normally operate, and the peak flux during the heavy time. So this is how you can, usually if you want to find, you can give the peak water flux will be given here, okay. Now here you see that this is the peak wet weather flow. When you use this peak weather flow, you don't use RAS here. Because why we don't use RAS? Because there's no return sludge in the case of MBR. So it happens only for the activity sludge process. Right? So that's why we only use the peak factor. So now once you find the total membrane area required, then you can find how much modules are required. That will be total membrane area divided by the area of one module. So that we did some calculation earlier. And the total gases required will be total membrane area divided by what's the total area of the gases. Okay. So that gives you the membrane, basic membrane calculation. The other thing that you have to do the calculation is the energy requirement. Okay, how much power is required because when you design the treatment plant, you have to know how much power is required. What's the power rating of your pump? How much power supply is required. So we want to do that calculation. So that all depends on all these various parameters mentioned here. So to do the calculation here, so the power required for aeration, actually in terms of kilowatt, will be the oxygen required per kg per day divided by the aeration efficiency. Okay, usually with aeration efficiency, which is how much kilowatt of energy can produce, that much amount of oxygen can be provided. So this usually aeration efficiency is given in the design standard, so you can use that one to find how much the power would be required to run a treatment plant, okay, for the bioreactor. So the first you calculate is SOR, which is specific oxygen required, that is in terms of kg of oxygen per kg of BOD. So the equation is given AOR into saturation dissolved oxygen, which is usually around 2 milligram per liter, right? Then there's a beta factor here and the alpha factor. So these are actually the oxygen transfer efficiency. So because whatever when you provide the oxygen in the aeration, it doesn't mean that your efficiency is 100%. So those things of effect here. So so these are the alpha is the oxygen transfer efficiency in the wastewater to clean water, and beta is oxygen saturation in the wastewater to so those sort of things affect. So these are some correction factor meters that we provide here, and the dissolved oxygen in the saturated zone and dissolved oxygen in the reactor zone. So this gives you SOR, specific oxygen ratio. Okay, so once you do that calculation, you want to find what was with the oxygen, because we need the oxygen requirement here. So oxygen requirement we calculated using this BOD loading rate, which is we already did earlier in terms of kg per day, and the SOR that we have calculated here. Okay, so that will give you the OR, oxygen required, and based on that oxygen required, you can calculate what's the power required. So once you get the power required, you know the reactor volume you have calculated earlier, right? So you can have a thumb rule, okay, this is the power. If you require 100 kilowatt here, and then you have 10 meter cube of volume, of 100 meter cube of reactor volume, so your specific power required is 100 divided by 100, okay? For 1 cubic meter of reactor volume, I require 1 kilowatt of power. So that sort of calculation you can, so that's called specific power required, okay? Any question after that? Okay, you seem to understand everything, okay? Yeah, of course, when you do that, the calculation yourself, it is not that difficult. So it's just a substitution of trying to understand which parameters what, okay? And all these parameters usually given, DO set will be given, zone will be given, beta is given, alpha is given. So you have to do some other calculations. So now total power required for the MBR wastewater treatment plant will be the aeration required in the reactor zone, okay, aeration zone. Also, if you put a separate aeration zone for the MBR, so you require MBR zone also, and also you require for flux management. Remember when I said that when you operate the MBR, you require some kind of source of coarse bubbling to scour the deposits that's on the membrane surface, and then to reduce the membrane fouling. So that's also required energy, is in the separate aeration air blower. So that's also cost. So this the total energy or total power required will be the combination of these three. Okay, so the power required for MBR zone can be calculated similar to the aerobic zone, but some of the parameters that's given for the MBR zone. And for flux management, usually there are some other ways of calculating, but usually we try to give you a specific power consumption. So for example, for flux management, to produce 1 meter cube of MBR per minute, you have to provide around 0.15 kilowatt hour of energy, blower energy, to reduce the prevent membrane fouling. So you can use this kind of equation to calculate the power required for the flux management. Okay. Okay, so now we have some options how to make this combination of advanced treatment water to make it possible for augmentation of water resources. Okay, if you don't have enough water resources, then people resort to treating the wastewater and then trying to augment the freshwater resources. You may not drink the water directly, but you may drink it indirectly. So it has happening in several countries. For example, is in happening in Singapore, one of the first countries to do that. So what they do is they have the conventional activity slash process. Now they have also even MBR. So they have primary treatment, then they have conventional activity slash process. And then after that, they process through microfiltration, okay, advanced, and then they have reverse osmosis treatment, very high quality water, and they disinfect it, and then they put it into the reservoir, freshwater reservoir, okay? So they don't directly supply this one as a drinking water. They put it to the reservoirs, okay? And they have a freshwater reservoir. So once it is mixed with freshwater reservoir, then it becomes a freshwater, okay? A part of freshwater. And then this freshwater is again pumped back to the water treatment plant, and then again further treated it, mixed with, because that now the water that you're getting is actually a mixture of the highly treated wastewater and the fresh water. So in that way, they indirectly actually, you can say it's just a bit of difference in time, but in a way you are drinking the wastewater, okay, treated wastewater. So that's how they treat that mix with the fresh water, treat it, and then and supply for the city. So that's one of the famous in Singapore. So that's how they sustain their water supply. And yeah, so this is how you can do it and what to reuse it using but addition of the membrane process into the conventional activity slash process. Or maybe you can completely remove the conventional activity slash process, replace with MBR, then you put RO, disinfect, and then you use high quality water. So this, what type of water can be used for, non-potable source, let's say purposes like toilet flushing, laundry, car washing, for the like for irrigation, and for in the Central Park that just in front of UTS, we have a water recycling plant where they use RO. And in block 3, Professor Sean will be discussing that one. So they have a water recycling scheme there. So they have all this, let's say, bioreactor, MBR, and then they go to RO, and then after that they go to UV, and then they supply it for non-potable purpose, like for toilet flushing and laundry. And then also they use it for they use it for the irrigation of the plants, in the ornamental plants that in the Central Park that they have, and also for the what's it, cooling tower. So they use it for various purposes. Okay. And also you can have a different other system here, one-step system, NF system. These are still in the research stage, where you can replace, you have alpha rehabilitation and directly use. Okay, this is okay, the similar to what we've already discussed. But here you can just replace MBR with, instead of UF, you can replace with NF or NF. Usually here people have tried using NF MBR, and then directly use it for some portable, but of course not really direct portable, but non-portable purposes, and after disinfection. So these are some of the options that is possible. Okay? So in your assignment, you are supposed to be designing this the process design. Okay, you have to give some options, what sort of combinations you can have to get water so that you can augment the freshwater resources. So this is the snapshot of the treatment plant in the Central Park, the wastewater recycling plant. So they have wastewater coming from the let's say restaurants and offices and the apartments here. Then it goes to screening. They have an anaerobic tank or anoxic tank here. Then go to the aerobic processing aerobic bioreactor here, and some chemical processing here. Then go to MBR. So they have a different chamber for MBR. And then after MBR, effluent goes to ultraviolet treatment, go to reverse osmosis, or some of them go actually directly discharge MBR effluent treated one, but of course they are using it all now. And then you go RO, reverse osmosis, and then high quality water after chlorination they supply back to recycle to the what's it apartment for toilet flushing and those sort of things. Okay, so this is how they use it for high quality water. So in that way, if you reuse the water, recycle the water, and then use it for other than drinking purposes, then you can significantly reduce your freshwater demand. Okay, for example, in Sydney, if the ordinary Sydney citizens are using like 300 liters per day of water every day per person, but because water is recycled here, then the fresh water that they require here per person is half. So only they require 150, not 300. So that's how you can significantly reduce by recycling the water, wastewater. Okay, so that was the MBR and the conventional activity/process and the MBR. Okay, so we just want to share some of the recent works that Sean and our group has been doing at UTS. It's called a source separation of urine. So if you remember in UTS FEIT building, the male urinals are waterless urinals. So they don't release they don't use water to flush the urinals. So the urines are collected from the male urinals, and this in the underground there are big large tanks that they're stored there. Okay, they store there, and then we separate from the going to the wastewater. So there are several advantages why we do that. So first of all, yeah, we do that research at the Center for Technology at Water and Wastewater under the School of Civil and Environmental Engineering and Faculty of Engineering Information Technology. We have 4 research teams that we work at CTWW in this center. So if any of you are interested in the future to do research, yes, please contact Sean and me and Leonard. So we're happy to be working. So there's a lot of facilities that we can do research related to water, wastewater, and any other environmental engineering related research. So why we want to do separate the urine? So there's some reasons. So for example, when you make fertilizer to grow food, right? We use a process what we call the Haber-Bosch process. It's a process of extracting air, nitrogen from the air, synthesizing and making into a synthetic fertilizer, urea. Okay, and then that urea we can grow food, and we eat the food. Then most of the nitrogen in the food, the fertilizer, is released in the form of urine, and then becomes a part of urine, become part of the water, right? And then we go to the wastewater treatment plant, spend a lot of energy here to treat the water, and then discharge, and still not able to remove a lot of nitrogen and phosphorus from here. We release it to the environment, cause a lot of environmental pollution. Yeah, so that's happening in the what we call it linear economy. So one direction. So just treat, bring the water, make the synthesize the water fertilizer, and then release to the environment. Well, we don't want that to happen. So that's called linear economy, because when you synthesize this fertilizer, it requires a lot of energy. It's estimated that around 2% of the world's total energy consumption actually goes to fertilizer industry. So there's a lot of emission coming out from the fertilizer industry. So why use? So if you look at every year the fertilizer consumption is going up, and then and okay, nitrogen is plenty in the air, but phosphorus is not. Phosphorus is quite limited. So if you don't recycle the phosphorus, then if it's only one way and extract from the mines and throw it as a wastewater, that linear economy is really going to create a fertilizer shortage in the future. So what happens now? What we are doing because when you look at it, most of the nutrient actually is in the urine. Actually, you will see that around 80% of the nitrogen that is coming to the wastewater treatment plant in the wastewater actually is coming from urine. So that's why we want to, instead of throwing to there, why not we recycle it back? Okay, recycle it back to grow food, urine. Okay, and even the nitrogen from the wastewater, you can recycle it back and then use to grow food instead of just throwing back to the environment, right? And then in that way, we can have less energy consumption for nitrification in the wastewater treatment plant, because when you remove urine, there's less nitrogen and phosphorus in the wastewater. So if you have less nitrogen, then you don't have to have a lot of aeration here to remove nitrogen. So in this case, you have to only remove the BOD, not all the nitrification. So that's why you can reduce energy here. And also we can save more, a lot of, you don't have to synthesize more fertilizer here because we can reuse it. So that's how we can do a new circular economy, recycle the waste thing, and then you can have a very clean environment. Okay, so that's the trying to convert from a linear form of nutrient economy to the circular economy. So you say, I just said around 80% of nitrogen that is present in the wastewater actually is coming from the urine, and around 55% of the phosphorus in the wastewater is coming from the urine, even though urine constitutes only 1% by volume. So if your wastewater is produced per person is say 100, your urine is only 1 liter. But you see amount of nutrient that is contributing to wastewater, that's quite significant. So if you remove that one or divert the urine from going to the wastewater, there's a lot of good things that we can do. So urine has a lot of, it says ammonia, a little bit of ammonia, but mostly in the form of urine or urea. So you'll see that 2% is a urea, and we have a lot of phosphorus, let's say potassium, sodium, a lot of other things also. And see, phosphorus, magnesium, calcium, everything is actually useful for the plants. That's why we have. And why urine is not used? Because urine is quite smelly, right? As I said earlier, urine is the urea. Fresh urine has urea, and with time, in the presence of enzyme called urease, it will convert into ammonia or ammonium depending on the pH. So that will be fluctuating, and it produces carbon bicarbonate. Okay, so this ammonia is the problem. So this is volatilization, is volatile compound, and that gives you a very pungent, unpleasant smell. So that's why people are reluctant and very saying yuck factor for the urine. And the dilution is, of course, and also the other problem is the volume. I mean, the urine volume, and sometimes we dilute it because people are using flush toilet, right? Urine flushing, and the urine can be significantly diluted. So that becomes a treatment, and concentration become a little bit tricky. And also if you use as a for growing food, also have some safety issues with the food, because it perceived that, okay, urine may be infected with some virus or bacteria, and then it may come to the food. So that's also perception is there. And of course, there's a high concentration of pharmaceuticals or micropollutants in the urine, because whatever medicine people take, it comes as a discharge as a urine. So that can have a little bit of problem. And also the other thing is the social acceptance, not able people to accept the water. I'm sure you learned this one in block 1, the public perception and the social acceptability. So it's still urine, to use urine as a fertilizer is still a challenge with the social acceptability. Okay, so yeah, these are some of the problem how urine has to be treated. So and also some of the solutions that you can see this read later on. And there are several advanced options people are now working to treat urine. So this Aurin is a good example that is being commercialized in the Swiss by the one group in Swiss who are doing very excellent research on this urine treatment. There are many different types of treatment technology being tried: thermal sterilization, freeze concentration, composting, urease inhibition, and this is the Aurin technology I was talking about. They use biological treatment processes and the thermal process together. And UGOL is another, using electrodialysis is one of our collaborators in University of Melbourne or the University of Queensland. They are working on that. And so there's some guys in India also who's working on trying to convert ammonia and then precipitate strubi and get the fertilizer. So our at UTS, led by Professor Hok Kyung Shon, we are working on this, what we call URBAL technology. Is a technology we use a membrane-based process to treat urine, and then convert it into concentrated fertilizer, and then you can sell it as a biofertilizer. So the process we use here is we have the urine collected from, say, for example, our building, FEIT building. You're using waterless urinals. We store in the basement, okay? And when it's stored, the urine undergoes hydrolysis. So with the enzyme urease, urea is converted into ammonia, right? And then we use that one to treat by the MBR, in membrane bioreactor. So we use as a submerged MBR here, during which we have the biological nitrification. That's exactly what we have in the conventional activity / process that happens here. So we have the conversion of ammonia, which is coming from the hydrolyzed urine, and convert ammonia into nitrate. So we have a nitrification process happening here. The difference between this and conventional activity / process would be that in this process, conventional activity / or conventional MBR, the other MBR, the difference would be the environment of the salinity. In this, the urine has a very high salinity because the total dissolved solid is much higher than the wastewater. Okay, wastewater may be up to maximum 1,200 to 1,000, right? The urine can be, the total dissolved solids can be like between 10,000 to 30,000 milligram per liter. So it's highly silent. Sometimes it's as close to seawater. Okay, so that is a challenge in the MBR. So the bacteria is not so fond of growing in the saline environment, but yeah, it takes time to grow. And then so this is how we do. After the effluent is treated, we use membrane distillation to concentrate. Okay, we vaporize the water and then concentrate get the concentrate which is highly containing a lot of nitrogen and phosphorus. So we can use this, what we call URBAL. URBAL means urine is valuable. Okay, so this is the acronym or the trade name we are trying to use. Okay, URBAL fertilizer. So this is very highly concentrated form of urine-based fertilizer that we can send it to ship it to any other countries, and then they can mix with irrigation water and use it for fertigation or irrigation. And the water that we get from the MD you can also use for potable or non-potable purposes. Okay, so this is the process that UTS has developed, and then we are working on it, and a number of PhD students are working on it now. So these are some of the experimental setup in the lab that you can find. This is the MBR in the lab scale. This is also MBR. So this is MD, the thermal distillation for concentrating the wastewater. Okay, so we get from here, this is your urine, okay, and this is the final concentrate, the fertilizer we get, and this is the treated water. So we have very high concentration of nitrogen and phosphorus here. Okay, so this is what we are trying to utilize as a part of the circular economy. We tested this one in various growing of different plants. Okay, here the lettuce and the pak choy, parsley, this kind of ripsalis trees species, and then parsley also in basil. So even this one Sean tried in his own decks here. So when we did all this testing using the fertilizer that we made from urine, yeah, it grows very well. It grows very well. Some of them grows even better than the commercial fertilizer. So we found that actually in the growth of parsley, the urine fertilizer is even better because urine has very rich nitrogen, so it can be very good for the leafy vegetables. So this also we have pilot plant. So this is the UTS FEIT building. We have all the male urinals are connected to collect the urine and then store in the basement. Okay, so this is how we are trying to do the research here now. Okay, we have this is the storage plant in the basement, and we have set up a pilot plant down there. Still working, our students are working on to treat the urine and then get the result that we want, and trying to test with the in collaboration with the City of Sydney and the Royal Botanical Garden. So this is the team that is to be working for our for the urine research. So I just maybe want to share that Professor Sean recently got quite a research funded by the Australian Research Council. And then so yeah, we are working on several themes: urine collection, urine processing, fertilizer optimization, fertilizer use. And so yeah, there are opportunities if some of you are interested in the future to do very serious research. Yeah, so you have opportunities that you can contact Sean or me or Leonard. So now comes the assignment. Okay, so how much we're doing? Okay, so we have some time. So let's, okay, so assignment scenario is given. Okay, the scenario is that there's a current wastewater treatment plant at Malabar. Okay, so they use a conventional activated sludge process, and but they don't have much space, and they want to upgrade it to a membrane MBR treatment plant from instead of conventional activated sludge process. So your job is to do some calculations, design calculation. You have to do process design, and then you have to do energy calculation, how much power is required and how much of footprint is required. So because when the difference between conventional activated sludge process and the MBR is that you save in one, which means the footprint. You significantly save in terms of footprint, but you spend more energy. So that's comparison you have to make. How much footprint you can save by putting the MBR instead of conventional activated sludge process, and how much energy, more energy you require in MBR compared to conventional activated sludge process. So these are the two main thing that you have to compare in your design. Then the next one thing you have to do is that you have to provide a process design. So you want to convert this one MBR into and or conventional activated sludge process into a design where you can augment the freshwater resources. Okay, same thing like a central park. Okay, that the Sydney is running out of fresh water, and then you want to use that as a resource to provide augment the freshwater resources for maybe non-potable purposes or for potable purposes. So that process design you have to come up and explain what is the significance of each of the process that you're putting. Because if I remember, if I shown earlier, there's several options you can for provide, right? You can provide NF, you can provide RO, you can provide UV, or you can provide ozone. What is it that you want to put, and then why you want to put that? So these are the explanation that you need to bring in the assignment too. Okay, so this is the assignment. So if you have any question now, this is the time to ask. What sort of you may have. We have Professor Sean also here. And yeah, if you want to ask any questions related to anything related to the subject, yeah, he's also there. Okay, so do you have any questions related to the assignment task 1? Of course, we have the let's say 1 week before, or I think 10 days before. 10 days before, I don't exactly remember the time that you have to look at in the date and time. There's a day where we will have a consultation before you submit your assignment, and then we have of course that time to thresh out if you have any issues related to assignment task 1. Task 2, sorry, task 2. Okay, so now is the time to ask any questions you have. Any question, Amit? Or
no, Professor. Actually, I haven't seen the assignment yet. So basically, I think I have to see that first before having any questions then. And if I have any kinds of questions regarding the lecture, then I think can I mail it to you for just some clarifications for that?
Yeah, sure. Yeah, you can send email, and then you can sometimes you can even contact through us. In the Microsoft Team, if you're using Microsoft Team, you
Yeah.
can leave message there also, or you
Yeah.
can send email also. So we have to anyway.
Okay. Okay. Sure. Thanks, Prof.
Okay. And I just want to tell you about when you write the assignment, try to write as concise as possible. You don't have to, because number of pages is we have given some, but it's not important. What is important is the quality of the content that you write. It's not also how much you write, because you can write many pages rubbish, but just write what is required. Yeah, very like one paragraph, maybe just 100 words or 200 words. That's enough to just convey the message. Okay, just important. Even you can in the form of bullet point, yeah, you can provide that, so you don't have to have it like a long essay. Okay, because it takes time for us to read also, and also when you don't, if you write something that is really not within the point that you are required to, then yeah, it's you waste your time and we waste our time also. Yeah, so try to write as concise as possible. And we will also provide some sample assignment samples. A few, I think 1 or 2 samples we'll provide. But most of the important things are blacked out, so you can get an idea of how the assignment looks, and then yeah, it should be okay for you. Okay, any questions? Jamming or rope or pulling chain? Do you have any? Henry, Ella?
No, that seems pretty reasonable. Appreciate the lecture.
Okay. Sean, you have any announcement to make?
So when is the next consultation timing?
Okay, let me see. I've sent the email.
Yeah.
Let me see the announcement.
So 2 weeks later, yeah.
Just hold on, Sean. I think it's around 2 weeks later. Okay. It's on 22nd of yeah, so it's 3 weeks after. Yes.
Yes, so I'm sure that they need time to prepare their assignment too, and that
Yeah.
they can come back to the consultation time, and then we can have more discussion. I'm sure that there's still some of students, struggling for the assignment one. So we will keep anytime. Yes, as you mentioned, you can send the email to Sharu and myself. So we are happy to continuously respond to you for the assignment too. So that's what I want to say, Sharu.
Okay. Okay. Thank you. Okay. So, anybody wants to raise anything?
Can I please ask, when is the assessment task going to be released? It doesn't show up on Canvas yet.
Okay,
Okay, so even assignment task for the block 2, assignment task 2?
Yeah.
I think it should be released, isn't it? It was already released. Let me check. It's already released, isn't it? Wait, assignments. Okay, it's not released. I'll just okay. Yeah. I will release it today. So I thought I already released it. It's not.
Thank you.
I'll check the content, because I have here. I have uploaded the file, but I have to make sure that I've uploaded the updated one, and then have it released in the next few hours. Okay, Ella.
Yeah, that's fine. Thank you so much.
Okay, no problem. Yeah, I didn't. I think I didn't release earlier because I don't want to distract when you guys are actively working on with the assignment one. So I think assignment one was submitted only yesterday or day before, right? So that's why I think we didn't activate it here. So I will release it by today. Okay. Any other question? Okay, so it doesn't seem to you don't seem to have any questions. But if you have any question, of course, just now we just did the lecture and then you haven't started your uh, the assignments yet. So as you start your assignment, then you will see okay what sort of problem that you may have. So then you can contact me anytime, Sean or me or yeah, and either Sean or me, so we can clarify your queries. That's all I have. So if Sean, if you don't have any other announcement to be made, maybe you can close the because we already, as we said, we'll do up to 2 o'clock. So it's 7 minutes past.
Yeah, I'm fine. Thank you, Sharon.
Okay, so please send me email if you have any questions. Okay, then I'm happy to clarify. So I'll see you during the consultation session on 22nd then. Okay.
Thanks so much.
Okay, bye.
Okay,
Bye.
thank you, Professor.
Thank you, Professor.
Stay safe.
Thank you.
Okay, where is my